Hi everyone, I hope everyone is doing well. In today's video, we're going to be going over a physical science paper 2 paper from November 2022. It is from the IEB, obviously, and it's the chemistry paper. So let's just a quick bit of with the instructions. They want us to do 2 decimal places, and that's about it. That's the only important instructions. And let's get into it. Here we have an unknown metal M forms the compound MSO4 which formula represents another compound where M has the same valency. So with these questions with unknown valency, what we have to do is we obviously need to determine the valency. But to do that, what we do is we write our two unknowns. Well, we write our two compounds that are, well, the two things that are being bonded together. So here we have unknown metal M, and we have our sulfate, polyatomic ion. And below them, what we do is we write the valencies. So we don't know what the valency of M is, so I'll put a box here. The valency of SO4, it's a polyatomic ion with a valency of 2. So it's -2, but we can just write 2. All right, and then what we normally do is to determine the chemical formula, what we do is we cross multiply. So the M will get the 2 and this SO4 will get this box, okay? So that's what we would normally do. So, but if we look at what we actually have, we have M, SO4, 2. All right. So what should this M have over here? If we cross multiply, you see the M should have a 2. So how do we get a 2 over here? You see how we have to multiply this whole line by 2. And if we multiply this whole line by 2, what we will get is we'll have M2 SO4 4. Okay, because we multiply everything by 2. Because previously there was a 1 here. Okay, there was a 1 over here. There's a 1 over here. But we know there should be a 2. Because when we cross multiply, there should be a 2. So we know it should look like this. Okay, so you can see now that this 4 over here, this 4 is the valency of M. So it should go over here. And the reason is if you cross multiply, the M will get the 2 and the SO4 will get the 4, like we have over here on this line. But what we do is we normally write it in the simplest ratio. And the simplest ratio is given in this line over here. Okay, so I hope that made sense. And let's have a look at it. So we know the valency of M is 4. Okay, so we need to find another compound where M has the valency of 4. Okay, so let's have a look here. Here we have nitrate, and nitrate has a valency of -1. So do you see how they're written in the same format? What we've given up here and here. But it can't be true because sulfate's valency is -2 and nitrates is -1. So there's no ways they can be the same. So we know it can't be A. Now we're working with M and phosphate. So if we compare M to phosphate, I said phosphate, but I started writing sulfate. Here's phosphate. Okay, and we know the valency of M is 4 and the valency of phosphate is 3. So to write the chemical formula, we would cross multiply. So the M will get the 3 and the phosphate will get the 4. So it would look like this. M3PO4, 4. Okay, because we cross multiply valencies. And do we have that? No, we don't. Okay, because careful, there's no bracket here with a 4. So don't let that 4 from the phosphate confuse you. So it can't be B. All right. And if we look at C, if we have M to oxygen, a valency of M is 4, valency of oxygen is 2. So if we cross multiply, we should be getting M2O4, which we don't get. All right, so it has to be D. And so you don't have to waste time doing that. I will show you though. We do have M and nitrate. So the valency of M is 4. And the valency of nitrate is, nitrogen. Sorry, I meant nitrogen. Okay, so the valency of nitrogen is 3. And if we cross multiply, we get M3N4, which agrees with D. So the answer here is D. In question 1.2, we're asked which one of the following contains 6,02 times 10 to the 23 atoms. All right, so this number should ring a bell. This number here is Avogadro's number. So if we have 6,02 times 10 to the 23 atoms, that means we'll have 1 mole, because if you look at the equation for the mole equation, you'll have N is equal to N, capital N, over Na. All right, so N is the number of particles. So it could be atoms, it could be molecules, it could be ions. So it's in terms of that, right? So that's what N stands for in Na. So in this case, our N in this case is the number of atoms. So very important, they're talking about atoms. All right, so we need to be very careful in terms of atoms. All right, you'll see where this comes into play. So let's just look at that. So this Na was familiar. It's also on your formula sheet. It's Avogadro's number. And that tells us when we have 6,02 times 10 to the 23 atoms or particles, then we'll have 1 mole of particles. All right, so if you're a bit confused, let's just look at the problem and hopefully it'll make sense. So we know we're working with 1 mole essentially, because we know that this number is equal to Na, but this is N. This thing over here is N, because this is our number of particles and it's related to Na. It's the same as Na. So in this case, they're equal. That's why if we do one of these, we're going to be getting 1 mole of atoms. Okay, because we're working on an atom basis. All right. So I hope you haven't been too confused. Hopefully the following explanations will help with that. Okay. So to work out the number of moles of argon gas, we're given its mass over here, M. We're given its mass. So what we can do is we can use this formula, M over molar mass, to find the number of moles of argon gas. So we know the mass is 18. And the molar mass of argon is 40. So we can see immediately this isn't going to give us 1 mole of atoms. 1 mole of atoms. Sorry, this should say mole. This should be mole. Okay. Now we know it can't be A. Let's have a look at B. So we have 5,6 decimeter cubed of ammonia gas. So the few of you that know off by heart your STP conditions or your molar gas volume, you'll know that if we have 22, so if we have 22,4 decimeter cubed, we'll have 1 mole of ammonia gas. Okay, so some of you might cross out this B, but you can't cross out the B because we're working on an atom basis. So let's have a look at that. All right, so if we work out the number of moles of ammonia gas, so NH3 gas, if we work that out, what we're going to be using is the molar gas formula. So it's V over Vm. Our volume is 5,6, and our molar volume is 22,4 decimeter cube. And if we work this out, we'll get that the number of moles is equal to 0,25. But we must ask ourselves, what is this? Moles of what? Is this moles of atoms, moles of molecules, moles of ions? And in this case, this is moles of, we should be saying mole, to be honest, mole. So this is 0,25 mole of NH3 molecules. So it's of molecules. All right, so some of you might be saying, okay, wait, but this isn't 1 mole. So this isn't going to give us, this isn't the same as Avogadro's number. Something's going on here. But we need to be careful. They ask of atoms. Okay, so this we've worked out, mole of molecules. Okay, so this amount of molecules. But the question asks over here for atoms. So how many atoms in 1 molecule of this nitrogen, this NH3? So there are 4 atoms, right? Because there's 1 nitrogen and 3 hydrogen. So if you add those, it's 4 atoms per molecule. All right. So if you want to work out the number of moles of atoms, you have to take the 0.25 times 4. And if you do that, you'll have 1 mole of atoms. Okay. And remember, 1 mole of atoms is equal to, this would equal Avogadro's number of atoms. So this is 6,02 times 10 to the 23 atoms. And all of this is related to this equation. So all of it is related to this equation over here. Okay, because over here we know the moles and we know Avogadro's number. Okay, so if we times those, we have 1 mole Avogadro's number. We'll know that the number of atoms, or particles, in this case atoms, will be equal to Avogadro's number. Okay. Next, we're given a solution of sodium sulfate, and it contains 1,5 times 10 to the 22 sodium ions dissolved in 500 centimeter cubed of distilled water. The concentration of sodium sulfate is. All right, so let's break this down. All right, so here we have sodium sulfate, this thing over here, sodium sulfate, and it contains 1,5. So the solution contains 1,5 times 10 to the 22 sodium ions. So very careful, sodium ions. Okay, so it's not, these are not the, so remember, again, we're using that formula. We're using that N is equal to N over Na. Okay, so in this case, this is the number of particles, number of ions, but of what? Of sodium. Okay, so we need to be very careful. It's not of sodium sulfate, it's of sodium. All right, so let's keep looking at this. It's dissolved in 500 centimeters cubed of distilled water. All right, this is problems, right? Because we're working with centimeters cubed. The SI unit for volume that we use is decimeter cubed. So we need to end up converting this. Okay, so let's convert it now. So to convert from centimeters cubed to decimeter cubed, we divide by 1,000. So our actual volume is just 0,5 decimeter cubed, cubic decimeters. Okay. All right, so we've broken down some of that. And now what we need to work out is a concentration of what? Sodium sulfate. The sodium sulfate solution. So do you see why I underlined sodium here and sodium sulfate? All right, it's quite important. So let's have a look. So we're going to have to work out, well, we're going to be using, we have to find a concentration. So the formula we're going to be using is concentration is equal to the number of moles over the volume. Okay, but we need to be very careful because we have to solve for the concentration of sodium sulfate. But currently what we can do is we can only work out the number of moles for the sodium ions. So we know the number of moles of the sodium ions. Well, we can find it using this equation over here. But this concentration needs to be for sodium sulfate. So this concentration needs to be for Na2SO4. So there's a bit of an issue here. So we need to actually find out the number of moles of the sodium sulfate. Okay, so first let's work out the number of moles of sodium ions. So we're going to use this equation up here. So the number of ions is 1,5 times 10 to the 22. And Avogadro's number is just on our formula sheet, 6,02 times 10 to the 23. Okay, that's the number of moles of, let me write it here, this is the number of moles of sodium ions. Okay, is given by this for sodium ions. So this is mole of sodium ions. And the reason I'm keeping it in this format is because if you look at the question, it's given, we don't actually work this out and put it in our calculator. We have to look at one of these and see how it matches. Okay. Very important now is this is for the mole of sodium ions. We need to work out the moles of sodium sulfate that we have. So we need to do a mole comparison. We need to use a mole ratio. Okay. So we have Na ions and we have sodium sulfate. This should be a 2 down here. All right. So we need to work out how many sodium ions go into one sodium sulfate, or how many Yeah, so how many sodiums end up becoming sodium ions? All right. Or you could look at it the other way. I was just being technically correct there. So if we look, how many sodium ions make up one sodium sulfate? So you'll see that we need to have 2 sodium ions, right? Because of this 2. We need to have 2 sodium ions to make 1 molecule of sodium sulfate. Okay, so now if we want to work out the moles of sodium sulfate, would you see how we have to divide by 2? We have to divide this thing by 2 because it's half. You see 2, you see 1 is half of 2. Okay, so to work out the moles of sodium sulfate, we know is a half of this number up here. So it's a half times 1,5 times 10 to the 22 over 6,02 times 10 to the 23. All right, and we're getting close. So we have the number of moles, but now we need to use this formula, okay? Because now we have the moles, not of Na, but of sodium sulfate, okay? But now we need to use the volume. Okay, so we're going to say concentration is equal to, and we're using this formula, number of moles, and we know the number of moles is this thing over here. So we're going to say 1 over 2 times 1,5 times 10 to the 22 over 6,02 times 10 to the 23. Okay, so that's our number of moles. And I'm showing this, let me not show it in another color. Then all of this is divided by our volume. In this case, remember our volume is not the 500, it's a 0,5 because it has to be decimeters cubed. So it's all over 0,5. Okay, so this is the formula for concentration that we have over here. All right, but the problem is it doesn't really look like anything over here. It doesn't really look. So what we need to do is we need to manipulate this a bit, okay? So we actually have to do a bit of maths here, which is often the case in physical science. So if we look, we have, I'm going to rewrite this as 1 over 2 times 1,5 times 10 to the 22 over 6,02 times 10 to the 23. Okay, and this thing is divided by 0,5. You with me? Because we have this top thing divided by this bottom thing. Okay, so that's exactly what I have here. But I can just use my rules of dividing. If I divide by something, it's the same as timesing by 1 over that something. Okay, this is just maths. Okay, so it's the same as timesing by 1 over that something. You with me? Okay, if you're struggling a bit here, it's have a look at your math stuff, okay? Because this is, yeah. So when we divide by something, it's same as timesing a 1 over that something. Okay, it's the tip and times rule from maths. Okay, and you'll see now what we can do is both of these are at the bottom. So what we can do is we can just times these at the bottom and times at the top. And what we're left with is 1 over 2 times by 1,5 times 10 to the 22 at the top, and at the bottom 6,02 times 10 to the 23 over 0,5. And now we need to see which one does this match with. Okay, so you'll see these ones are slightly different, but the only thing that's different is this 1 over 2 can move to the front. All right, so we know it has to be A or B, and it can't be C or D because these have 2 in the front and not 1 over 2 in the front. Okay, so it has to be between these two. And you'll see it can't be B because it's the opposite. It's this thing flipped that we have. So it's not B and it has to be A. So 1.3 is A. All right. Now for 1.4, it says which of the one of the followings has polar covalent bonds but has London intermolecular forces. Okay, so we have polar covalent bonds but London intermolecular forces. London intermolecular forces. Okay, which is interesting because when we have London in intermolecular forces, it's induced dipole forces. So induced dipoles when we have non-polar molecules, all right? But it's possible to have polar covalent bonds, but non-polar molecules, okay? And that has to do with molecule shape, molecular shape. All right, so if you're not so familiar with molecular shape, I encourage you to revise that. But if you want to have a molecule that's non-polar, okay, so a non-polar molecule, right? So let's have a look. Let's look at an example. So we have carbon dioxide. Carbon dioxide is given by this shape, okay? This shape is linear, okay? So this is a linear shape. So I'm going a bit on a tangent with a bit of a lesson here, but I'm sure it'll help, at least someone. All right, so this molecule is linear from this shape, all right? So this molecule is linear. But the thing is, it has polar covalent bonds because carbon has an electronegativity of 2.5, right? So it has an electronegativity of 2.5, and oxygen has an electronegativity of 3.5, all right, or 3.5. Let me use commas, 3.5. So you see how these bonds between these two are polar. So it has polar bonds, but because it's linear, the fact that it's linear means that the molecule is nonpolar. The entire molecule is nonpolar. Okay, so that's important. Symmetrical molecules, so like linear, symmetrical, any symmetrical molecule will be nonpolar. All right, so any symmetrical molecule will be nonpolar. Okay, and if we look at the symmetrical molecules, or symmetrical shapes rather, the symmetrical shapes are linear. Well, the ones that you need to know for the IB exam. There are more, but it's linear. Should have used the other color, but we're rolling with it. It's linear. There's trigonal planar. Trigonal planar. And finally, there is tetrahedral. Okay, so if any of these molecules have these shapes, then we know that the molecule will be nonpolar. So there's two conditions we need to meet here. First, it has to be polar covalent bond. So there has to be a difference in electronegativity. And the second condition is you need to have London intermolecular forces. So the molecule has to be symmetrical. It has to be nonpolar. Okay, because there can't be dipoles in the molecule, in the overall molecule. All right, so there's two conditions. So it has to be a polar covalent bond and it has to be a symmetrical molecule. All right, so if we look at phosphorus and hydrogen, if you look at your periodic table, you'll see that they have the exact same electronegativities. So this is a non-polar covalent bond. So it doesn't meet condition 1. So we can cross it out. All right. Then for B, if you look at the electronegativities, you'll see between carbon, hydrogen, and chlorine, you'll see that there are indeed, there is indeed an electronegativity difference. But the thing is with this molecule, it's not symmetrical. So this is important. The shape is symmetrical, right? Because this molecule is tetrahedral. But can you see why it's not symmetrical? You see how we have this random chlorine? We have hydrogens and then a chlorine. So we got this like imposter chlorine that will like make the molecule not symmetrical. And obviously, I mean, if you have carbon, so if you have carbon, you have a hydrogen here, hydrogen here, and a chlorine, is this thing symmetrical? No, definitely not, right? Because you got this random chlorine over here. So it can't be B because the molecule is not symmetrical. So important, it has a symmetrical shape. This molecule is tetrahedral. But because this chlorine is not here, this molecule is not symmetrical. Okay, you can see if I draw like an invisible line of symmetry down here, if you try to fold the molecule, it won't be the same. Okay. Now let's have a look at these last two. So both of these last shapes are tetrahedral. Okay, and they are both symmetrical. So they're both tetrahedral and they're symmetrical. So unlike this one where we had 3 hydrogen and chlorine, these are 4 chlorines and these are 4 iodines. Okay, but so they both meet condition 2. But let's see which one meets or doesn't meet condition 1. All right, so carbon and chlorine, they do have an electronegativity difference. So they are polar. So the bond is polar. So we know immediately it's C. And the reason it's not D is because iodine and chlorine have the exact same electronegativity. So the bond between chlorine and iodine is non-polar. So it doesn't meet condition 1. So for the answer there is C. All right, that was a lot, but I hope you stuck with me. I know that a lot has been going on in this multiple choice, and yeah, I hope you've been sticking with me. A quick little detour. I just want to say I'm doing a lot of working for these multiple choices, but I'm doing that to explain the thinking behind the problems. I really don't want you, it's really important that you don't spend too much time on these, okay? So there will be times when you can cross out things immediately. You'll see in some of the questions where we know things are bogus already, but for some emphasis, I am going through all the options that are not, sometimes I'm going through options that are not relevant. So in your tests and exams, make sure in the multiple choice section, you're not writing full formulas like I was doing and things like that. Make sure you're doing shorthands. You don't have to show the full formula and plug in, substitute, formula, answer, units. Make sure you're going quickly, but make sure you understand what you're doing. And very important, cross out things that are nonsense. Cross out things that you know are not true. They cannot be true. They don't make sense. Like for example, above here, we know that B does not make sense immediately because it's not symmetrical. So you don't even have to do the electronegativity test on B because we know it's not symmetrical. Okay, you with me? I want you to take careful note of what I just said about crossing off bogus answers in question 1.5 over here. Let's have a look and keep an eye out for that. So we have the catalyzed formation. So this is probably going to be important. Formation of ammonia by the Haber process, and it's given by this equation. And we can see that the forward is exothermic. All right, the forward reaction is exothermic because the change in enthalpy is negative. Okay, so I'll write that the forward is exo. All right, or what you can do is you can just write here exo and at the bottom endo. All right, sorry, I know my E's are super small there. But anyways, so let's have a look. Which change in reaction conditions will increase both? So there's two things here. So what will increase the rate? So this is condition 1. And the equilibrium yield of ammonia, 2. So what they mean by equilibrium yield is they just mean which one is going to favor ammonia more. So which one of these is going to favor ammonia more? Okay, so let's have a look. So let's have a quick scan through. We see here increase in surface area of the catalyst. So what do we know about catalyst? Catalyst will increase the rate of formation of both the forward and the reverse. So it meets condition 1. But because they both increase equally, there will be no shift in equilibrium. So we're not going to be favoring the forward. So because of that, we know it's not D because it doesn't meet condition 2. All right, then let's have a look here. A decrease in temperature, increasing rate. No. A decrease in temperature will always decrease your rate of formation, always, right? Some things will be favored, okay? But a decrease in temperature will always decrease your rate of formation. They will both decrease. One will decrease less than the other, okay? So I hope I made sense there. That's got to do with Le Chatelier. But a decrease in temperature will always decrease the rate of formation. All right, so we know immediately it's not A. And you see how quickly we've crossed out 2 answers. All right, so let's have a look. Now let's have a look at B. So we actually now going to analyze B. So you see how we've not waste any time analyzing A or D, any thinking. We're just like, whoa, that's definitely not true. That's definitely not true. Now we're doing a bit more thinking for B. So an increase in temperature. An increase in temperature will increase rate of formation of both the forward and the reverse, right? Because increase in temperature, you're going to be having, because of the collision theory, you're going to have more effective collisions, things like that. So the rates of both will increase, okay? But the equilibrium yield of ammonia. The forward reaction is exothermic. So if you increase temperature, what reaction will be favored? The reverse, the endo reaction, the endothermic reaction. So that means at equilibrium now, we're going to be having less ammonia because the reverse is favored. So there's going to be less ammonia. So we don't meet condition 2. We're not going to we're not going to increase the equilibrium yield of ammonia. So we know immediately it's not B. And we don't have to do any thinking because we've crossed everything else. It's C.
Hey everyone, this is a message from the future, editor Brandon over here. So I really messed up the wording here for my explanation on part C. Okay, I confused pressure and temperature, but let's just talk about it. So in my explanation here, an increase in pressure is going to favor, according to Le Chatelier, the system going to try to relieve the stress by decreasing the pressure, right? And the thing that will decrease the pressure is the reaction that produces fewer gas molecules. And that is the forward reaction, because the forward produces 2 and the reverse produces 4. Okay, so it's that 3 from hydrogen and then the 1 from the nitrogen, because remember there's a 1 in front there. So that's why the forward is favored when you increase pressure, and that's why the equilibrium yield of ammonia will increase. And obviously also we know one of our from our rates of reaction, we know an increase in pressure will increase the rate of reaction for both the forward and the reverse. It's just the forward will increase more. Okay, so we meet both conditions there.
In question 1.6, we're given the Maxwell-Boltzmann distribution curve for a reaction mixture. That's shown up here. And it says now the concentration of the reaction mixture is now increased. Which one of the following shows the net distribution curve as a dotted line? All right, so let's cross out some things. So A is what happens when we have a decrease in temperature. Okay, so the kinetic energies drop and the graph increases to keep the same area. So we know it's not A, because this graph is for decrease in temperature. And we know it's not C, because this is a graph for the increase in temperature. Kinetic energy shifts to the right and shifts down to keep the same area. So it's between B and D. All right. D would be if you decreased the temperature and took molecules out. But you don't have to know that, right? But you can see D is a bogus thing, because A, I've been saying bogus a lot in this exam paper. Sorry, I hope it's not triggering anyone. But anyways, so D is this weird thing, okay? Because we haven't seen this before. You shouldn't have seen this in your theory, okay? You don't have to know this. So there's some weird things here. So we know it's B, okay, just by the process of elimination. So now, again, we've crossed out things, but let's look at the explanation, just so everyone understands what's going on, if you were confused by the crossing out. So if the concentration is increased, you're going to be having more molecules per unit volume. And that's what happens. So you're not changing the kinetic energy of the molecules at all. And you'll see here, this kinetic energy is the same. So this peak is the same. The thing is, all your kinetic energies, they don't change, right? They're just the number of particles moves up. So you see all these kinetic energies are the same. They're not shifting, but you're just having more particles, okay? You're having more, because remember the area of a Maxwell-Boltzmann distribution represents the total number of particles. And you see how there's bigger area in red than there was in this one below. I'm going to shade this one below in blue. You see this one below. You see how we have more area in the red than in the blue. Okay, and that makes sense because we're having more molecules per unit volume. But they're at the same kinetic energy, but just higher. Okay, because there's going to be more particles, right? So say this is some random like number like 50 perhaps, and you see how this one would have been maybe like 40. So you see how the number of particles is higher. Okay, so we're going to be having more particles. That's why the graph just shifts up. Okay. Here we're given this reaction. It's between hydrogen and iodine, and we form this thing over here. And it says the Kc of this reaction is X. And it says, what will the Kc value for the reverse reaction be when the volume of the container is halved at the same constant temperature? Okay, so immediately cross this out. The volume of the container is halved. Why? Why can we cross that out? Well, Kc, the equilibrium constant, depends on one thing and one thing only, temperature. And the temperature is constant. So we don't even have to worry. This is bogus, what I've been saying. This is bogus. This volume of the container is halved. You see, I put so much bogus things in here, it's annoying me. That's why I'm talking about bogus things. But anyways, the volume of the container is halved. It's bogus. We don't care about that, right? That just means the pressure is going to increase. But we don't care about pressure because the only thing that Kc depends on is temperature. And we have a constant temperature, okay? So now some of you might be thinking Kc is the same, all right? So some of you might be looking here at A and saying this is an attractive option over here. But careful, what did they put in all caps? All caps. They didn't bold it, but they put in all caps. The reverse reaction. Reverse. Okay. So remember the Kc for the forward reaction is given by the concentration of the products which is this, over the concentration of the reactants, which is this. Okay, but now for the reverse reaction, you're just going to flip this thing, right? Because your products now become your reactants and vice versa. Okay, so the Kc, this is for the forward, and for the reverse reaction, you should know this from your theory, but also we can have a look at it here. Kc for the reverse is now H2 and I2 over Hi to the power of 2. All right. So if you have a look at this thing here at the top, this is equal to x. And this thing is just the inverse of x. So you see how this thing has to be 1 over x. And that's why the answer here is D. Okay. So you see how important it is in the multiple choice things. If you want to be efficient with your time and get to the right answers, you have to cross out all the things that are useless. They're there to misguide you in a way, but they're there to throw you off. Okay, cross that out. Don't let that cloud your brain. Don't waste precious mental energy trying to figure out these things. Okay, or trying to process these things that are trying to confuse you. Okay, so I know I've been ranting about that a lot, but I hope you can tell that it's super important because I've been ranting about it a lot. All right. So here for 1.8, how many straight chain esters are there with molecular formula C4H8O2? All right, let's draw one. Let's draw an ester. So here's an ester. Okay, I'm not going to be filling in the hydrogens. I'm just going to be doing these. Okay. So there would be hydrogens over here. Okay, so remember we split esters about this oxygen. Okay, so everything to the left here comes from an alcohol, and everything from the right comes from carboxylic acid or carboxylic. I might say either or, but carboxylic acid. Okay, so if we look at this, let's have a look what can happen. All right, what can happen is, you don't have to draw this. I'm going to draw it for you, but you can see that one of these carbons can be chucked to the other side. Okay, so, well, let's look at it this way. This carbon can move all the way to this side. I'll draw it in a second, but this carbon can move all the way to this side. All right, so that's one option. Okay, another option is this carbon can move all the way to this side. And third, a final option, this one can move also to the other side. But let's have a look. So I know there's a lot of weird drawings going on over there, but let's have a look. So this is one option. Okay. So I did mess up over here. I did this carbon, you can't move both of them. Okay. I did mess up in the explanation, but things will be clear now. Okay. So I can have 2 carbons on the left. Another option is I can have 3 carbons on the left, like this. All right. This still works, and your hydrogens would be here. So this works, right? So now we have 2, and finally, so we had 2 on this side, and we had 2 carbons on the left. Now we have 3. We can't have 4 on the left, okay, because this carbon can't move. But what we can have is just 1 on the left. So it would look like this. Okay. And if you count the hydrogens, you'll see that we meet this condition over here. All right. So this one will have 4 carbons. We can actually check. So it has 1, 2, 3, 4 carbons. And it'll have 8 hydrogens, 1, 2, 3, 4, 5, 6, 7, 8, and 2 oxygens. Okay. And they all meet that criteria. So the answer here is B. There'll be 3 straight chain esters. Okay. So sorry about my mis-explanation about here in the beginning, but I hope my drawings fix that for us. Okay. All right. So, which one of the following organic compounds does not contain oxygen? Speedrun. Okay. Pentanol, oxygen. It's an alcohol, has that. Butyl propionate, it's an ester, has oxygen. Methanoic acid has an oxygen. Okay, so it's A. All right. Let's just take a bit of a quicker look at that. So pentanol is an alcohol. So we know it's going to have that alcohol group, right? That hydroxyl group, all right? Butyl propionate is an ester. We just drew an ester, but we know that esters have the what do you call it? The functional group of this. This is the ester functional group. Okay. So you can see immediately it's got 2 oxygens. Methanoic acid, again, functional group like such. All right, so you can see how those 3 all have oxygens, so it has to be A. A is just dibromo-octane, so it's just carbon, hydrogens, and 2 bromines. Sorry, carbon, hydrogen. I don't know if I said oxygen there. So it's carbon, hydrogens, and 2 bromines. So you see how A does not contain. So important, does not contain. So A does not contain oxygen. All right. So again, I'm trying to highlight how you don't spend too much time when you don't have to. You don't have to draw pentanol. You don't have to draw butanol propionate. Okay, don't waste your time, guys. It's super, super important for the multiple choice. And a lot of people do the multiple choice first, and then to be confused and wasting all your time and then looking up at the clock, it's just going to throw off your whole paper. So please, guys, I know I sound like a broken record, but please, please, please use your time well. Okay, don't waste time in the multiple choice because it has serious knock-on effects with the rest of the paper. Okay. All right, let's have a look. Which option correctly shows a positional isomer and a chain isomer of the compound pent-1-ene? All right. So we need to know what a positional isomer means. So a positional isomer is the same functional group, but you're just moving the location of your functional group. So here we have pent-1-ene. So if we move that, it's just a double bond. It will either be in pent-2, so it can move to pent-2. You with me? Okay, so that would be a positional isomer. So it's still pent, but now we're moving this 1, so it can move to a 2, second position. Okay, a chain isomer is the same molecular formula but different length of chain. Okay, so pent is 5 carbons, and in a chain isomer we're no longer going to be having 5 carbons. We're going to have a different chain. So it's going to be a 4, like for example, a 4 chain carbon, but there's now going to be a branch, an alkyl branch. Okay, so it's a different size chain. So instead of the 5, like for pent, it will now be 4, 3, 2, etc. Okay, so immediately we can cross out A and C. And the reason is because these are different chains. Here we're working with pent, and here they're talking about bute. What is going on there? No, it's B and D. Okay, because it's pent and the double bond is moving. So it was in the first carbon, now it's on the second. All right. Now we need to do a bit more thinking on the chain isomers, but we actually don't even have to do more thinking because look, it's bute-1-ene. So somehow pent-1-ene is 5 carbons. Bute is 4. So a chain isomer, we have to keep the same molecular formula. We can't just chuck off a carbon, right? Because that's not an isomer. This is something completely different. Okay, because this is 4 carbons. So we had 5, now we just got 4. You can't drop that, okay? So we know it's not B, it has to be D. And the reason is here's 3-methyl bute-1-ene, okay? So it's the same molecular formula, but now you're just going to have a chain of 4 carbons instead of 5. And on the third one, you are going to be having, so there'll be a double bond here. And on the third one, you are going to be having a methyl, a chain like this. Alkyl group like this, rather. A branch is what I meant. So, yeah, so you see how we still have 5 carbons, okay, and we still got our double bond, but we got this thing that's now a different chain, because there's a chain of 4 instead of a chain of 5 with pentene, rather. You with me on that one? Okay, so it's D. And that concludes our multiple choice. Okay, so the multiple choice is 20 marks out of 200. The paper is out of 200. All right, so consider that, and also consider that in terms of your time. How much time you're going to spend on multiple choice. In question 2, we're given these 3 diagrams. They say the intramolecular bonds, so careful, the intramolecular bonds are represented by solid lines. So these solid lines are intramolecular bonds. So intramolecular bonds are between atoms in the molecule. So you see we have an atom of hydrogen, an atom of oxygen, and they're bonded with this solid line over here. So that's intra, so within. But then they say the intermolecular forces, so these intermolecular forces are represented by the dotted lines. So these dotted lines. So there's no actual bond. It's just a force of attraction. So intermolecular forces, so between molecules. So you see here is 1 molecule of water, Here's another molecule of water, but this dotted line over here is a force of attraction between the molecules. So that's intermolecular forces. Okay. So we're given these three things, and they say it's a 2D representation of a 3D reality. Study the diagram and answer the question set. So they say here the solid lines represent covalent bonds, and they ask us to define a polar covalent bond. So a polar covalent bond, according to the SAGs, is just something you have to remember. It's an unequal sharing of electrons leading to a dipole forming. So I'm not going to write that out in full, but it's an unequal sharing. And what that happens, that causes a dipole to form. All right, there is a document on my website. You can find the link on my channel. And under downloads, I have all the definitions from the SAGs, and I put them in a table format. So it's a bit easier to read and a bit easier to find than just looking through the SAGs. So these SAG definitions you can just find on my website or just the SAGs themselves. So that's why I'm not going to write out the whole definition here. But polar just means an unequal sharing, and that leads of electrons, and that leads to a dipole forming. So that's the SAG definition there. And then here they say between which two atoms is the polar covalent bond the least polar? All right, so let's have a look here. They say between which two atoms is the polar covalent bond the least polar? So the least polar, so how do we determine a polar covalent bond? That's with the difference in electronegativities, right? So the one that has the lowest difference in I can't speak. The lowest difference in electronegativity will be the least polar bond. So we have to consult our periodic table. Let me pull it up for us. So if we consult our periodic table over there in the top right, let's first have a look. So we have hydrogen bonded to oxygen. So if we look at the electronegativity difference, we'll see that hydrogen's got here 2.1 and oxygen's got 3.5. So that leads to a 1.4 difference. So that's a difference of 1.4 between oxygen and hydrogen. So let's remember that. And then let's check now between, we also have over here, we have carbon to hydrogen. So let's see the electronegativity difference between carbon and hydrogen. So hydrogen is still 2.1 and carbon's 2.5. So that's a difference of 0.4, which is lower than what we just did for hydrogen and oxygen. Let's check again for what else we have. We also have carbon to oxygen over here. We have carbon here and oxygen here and a bond there. So let's see with that one, carbon's 2.5 and oxygen's 3.5. So we see that the least polar, so the lowest electronegativity difference is between carbon and hydrogen, because hydrogen's 2.1 and carbon's 2.5. So it's a 0.4 difference. So between two which atoms, we would be saying between hydrogen and carbon. So you don't have to show it like this. You could also say carbon and hydrogen. And why is it the least polar? Give a reason for your answer. And we said that it's the smallest difference in electronegativity. So the smallest difference. So the smallest difference in electronegativity. Okay, sorted. Now, so they say the dotted lines represent hydrogen bonds. So let's have a look at that. So just these dotted lines are hydrogen bonds. And remember, hydrogen bonds are intermolecular forces. All right. So they say state 3 requirements for the formation of a hydrogen bond. So this is just theory. It's something you should remember. I do have a short video on TikTok where I do, in 30 seconds, I do give you this theory. But we know hydrogen bonds are they're usually between these 3 in the top right, between nitrogen, oxygen, and fluorine. So between these, you normally have hydrogen bonds. So NOF. But they're not asking for those. They're not saying between which 3 elements, right? They're saying the 3 requirements. So this is just theory you need to remember. So the first thing is you need to be having a small atom. Okay. So hydrogen has to be bonded to, so we should actually be saying here. So hydrogen is bonded to. Okay, so when hydrogen is bonded to a small atom, and then the next thing is of high electronegativity. So a small atom with high electronegativity. And then the third point, so there's 3 points for 3 marks. The third bullet point is with at least one lone pair of electrons. All right, so if we meet these 3 conditions, we'll have hydrogen bonds. But let's just have a look. You can see here, nitrogen, oxygen, or fluorine, they're high up in the periodic table. So they have small masses, right? So they're small atoms, okay? So they're on the second period over here. So the second line, so they're small atoms, okay? So they all meet that criteria. They all have high electronegativity, so 3, 3.5, and 4. And they also, well, you can't see it here, but they have at least one lone pair of electrons. And we can see that. So it's not a given from the periodic table, but we can see here that oxygen has, if we look over here, you see how oxygen has one lone pair of electrons. So that's why it's able to have this hydrogen bond over here. Okay, so those are the 3 requirements. And now they say, why are hydrogen bonds stronger than dipole intermolecular forces? So we've touched on 2 of those points here already. Okay, so remember, this is theory. And what we need to be saying is hydrogen bonds are stronger than dipole intermolecular forces is because, well, in this case, the oxygen-hydrogen bond is very polar. It's very polar. Okay, because remember, it's very polar because these have high electronegativity. So the electronegativity difference is going to be high. So the bond is going to be very polar in comparison with least polar that we did before. So that bond is very polar, and that means there are going to be large dipoles. Okay, so it's very polar, so there's going to be, so that leads to strong dipoles. Okay, so sometimes I write shorthands like this arrow means leads to. Make sure, I don't want to write everything here, it will take too much time, but make sure you listen to my answers and the full answer, okay? So make sure when you answer your paper that you're writing in full sentences. So the OH bond is very polar, and that leads to, that arrow, strong dipoles forming. Okay, so that's our first point for 1 mark. And then the second thing is that the molecules get close together, all right? So because it's a small atom, so first we discussed this point in our first bullet point. Now we're going to discuss this one, that it's a small atom. So there's 2 reasons. So firstly, it's this high electronegativity. And then the small atom part is that the molecules can get close to each other. Okay, so we can say molecules can get close to each other. All right, so you see how the reasons why hydrogen bonds are stronger than dipole intermolecular forces are related to the 3 requirements of hydrogen bond formation. All right. Okay, now what we have to do is we have to circle the words from within the brackets in the statement below. So boiling is a physical or chemical process in which intramolecular bonds are broken or intermolecular forces are overcome. All right, so in boiling, okay, let's say, for example, we're boiling water. So we have here, this thing here at the top is water. So if we boil water, what happens is these molecules, let's assume this is a liquid. So when we boil it, now water is going to spread far apart, right? So before it was liquid, they're kind of just like this. They're kind of free to move over each other. But in a gas, what happens is now they move far apart from each other. Okay, so this was for a liquid over here, and this is for gas up here. So do you see there's no chemical process going on? It's not like we're making something new. This is still water. But what's happening is we're physically separating them. So it's not a chemical process. We're not making bonds or mixing water with something else. It's just a physical process, okay? Physical separation. So my circling is terrible, so I'm going to square it, okay? But make sure you circle it. And intramolecular bonds. When we boil, right, are we breaking the bonds between oxygen and hydrogen? No, we're just breaking these bonds over here between the molecules, right? We're overcoming, we're not breaking them. There's no bonds to break. The forces, these forces of attraction are being overcome, right? So these forces need to be overcome so this water molecule can move away from these two. Okay, so that's why it's a physical process in which intermolecular forces are overcome. Okay, they asked for circle. They said circle, so make sure you circle. I'm not going to do that because my circling is terrible. All right. Okay. Now, explain fully why water has a higher boiling point than the other two compounds. Make specific reference to the diagrams. Okay, so this is one of those where we're talking about boiling point. So there's a very specific formula or steps we need to follow. So let's go to those steps. Okay, so first let's have a look. Water has a boiling point of 100 degrees up here, but methanol has 64 and ethanol has slightly higher, it's 78. So you see water has stronger intermolecular forces. But let me clear all of this and let's see what's happening. So when they ask about boiling point, so the process is we identify forces. So the intermolecular forces. So I'm just going to say the forces, okay, for intermolecular forces. First step, we have to identify intermolecular forces. Then we talk about strength. So which ones are stronger, okay? And third, we talk about energy. And then four, we make a conclusion. Okay, so conclusion. In this case, our conclusion is going to be related to boiling point. All right, so in number one, you can talk about the type. You can either say so you have two options. So option one is you can say the type of intermolecular force, or you can talk about the number, because sometimes they have the same type of intermolecular force, but a different number of regions, okay, where that force takes place. So let's have a look. So we know that these dotted lines represent hydrogen bonds, okay? So let's have a look at a water molecule. Let's look at this one water molecule. Let's see. So we know it has hydrogen bond forces of attraction. But you can see here that these dotted lines represent intermolecular forces. And can you see that one water molecule has how many regions where it has hydrogen bond forces of attraction? You see it has 4. Okay. So one water molecule can have 4 hydrogen bond forces of attraction per molecule. All right. Let's look at methanol. All right, let's look at this methanol over here. So if you look at this methanol, you can see that it only has 2 regions. It has one here and one here. So one methanol molecule can only have 2 hydrogen bond forces of attraction per molecule. And the exact same thing here for ethanol. Here's a molecule of ethanol. And around this molecule, it can only have 2 hydrogen bond forces of attraction here and here. Okay, so water can have 4 hydrogen bond forces of attraction per molecule, whereas methanol can have 2 and ethanol also only has 2. So we need to reference that, okay? So what we're going to say is water is going to form 4 hydrogen bonds with neighboring molecules, okay? So water forms here. Okay, so water forms 4 hydrogen bonds. Hydrogen bond forces of attraction, so forces of attraction, that's what that FOA stands for. Water forms 4 hydrogen bond forces of attraction per molecule. So per molecule. And then here we're going to be saying, we now need to compare it, and the other 2 molecules have 2 hydrogen bonds per molecule. So you'll say other 2, so again, I'm writing short form here. So the other 2 molecules, they have 2 hydrogen bonds, forces of attraction, hydrogen bond forces of attraction per molecule. Okay. And what we can say now is that water is going to be having stronger intermolecular forces. So we can say, therefore, water has stronger intermolecular forces, so stronger IMFs, intermolecular forces. So we've addressed bullet point 2 now. We talk about strength. Now we need to talk about energy. So now we're going to say, therefore, more energy. So more energy is required now to overcome these stronger forces of attraction. So more energy required to overcome. So this overcome part is really important. So more energy to overcome is really, really important. You need to have that specific wording, okay? So more energy required to overcome the stronger intermolecular forces. So the stronger IMFs. And then finally, for our fourth step, we're going to have our conclusion, and therefore water has higher boiling point. Okay, so you see I was a bit extra here if you're comparing with the memo, but I'm just being safe. You'll see the memo didn't include this step over here. But I like to follow this 4-step process on the right. I find it to be quite helpful in a lot of different places. Okay, let's go to the next question. They say ethanol has a higher boiling point than methanol. So let's confirm that. Where is it's up here? Okay. So if you look here, here's methanol and here's ethanol. So they both have two places where hydrogen bond forces of attraction take place, but ethanol's boiling point is higher. Okay, so they've said that, and they say which type of intermolecular forces are predominantly responsible for this. Okay, so we see methanol has 1 carbon and 4 hydrogens, and ethanol has 2 carbons and 6 hydrogens. So ethanol is a bigger molecule. Okay, so here we should be realizing we're dealing with London intermolecular forces. So we can say London forces. So there's 3 things you could say. It's either London, dispersion, or induced dipole. So they all mean the same thing. So only put one. So you can either say induced dipole, dispersion, or London forces of attraction. So don't put all 3, you can choose one. They all mean the same thing. Okay. Now they say explain why the intermolecular forces are stronger in ethanol than methanol. So there's 3 reasons we need to talk about. Well, there's 3 possible reasons. Because the mark allocation here is 2, you only have to give 2. But there are 3. So I want to discuss all 3 because they're all relevant and it's important to know. So let's have a look. So because ethanol is larger, right? So it's a longer chain. So because it is so one of the reasons is you can say it has a longer chain. All right, so it has a larger interacting surface. So that's one of the reasons. So let's write that. Okay, so this is one of the reasons. So it's a larger interacting surface. So here you will write ethanol. So ethanol has a larger interacting surface area. Okay, or you could say longer chain. Okay, so that's our first reason. All right, so I'll label it 1. Then our second option is what we can say is that ethanol is going to have more electrons. Okay, obviously because you're adding carbons and hydrogens, that means you're adding more electrons. Okay, so ethanol will have more electrons. So ethanol, that means more electrons. So ethanol has more electrons. Okay, you could also say that it has a larger electron cloud. It's up to you there. So over here, if you just had those 2, you would get 2 out of 2. But let's look at the third reason as well, is that ethanol, because it's a larger chain and it has more electrons. So it either forms, you can say it forms larger temporary dipoles or it forms more. All right, so we would say ethanol again. So ethanol, this double dash just means it's the same thing. So ethanol forms larger. So you can say ethanol forms larger or more temporary dipoles. Okay, remember, don't put the slash. Don't use the slash in your test or exams. You can either say it forms larger or it forms more temporary dipoles. temporary dipoles. All right, and that was it for question 2. Let's have a look at question 3. So they say nitrogen monoxide gas may be prepared by adding copper metal to dilute nitric acid. The balance equation for the redox reaction is given below. Okay, so we're given this reaction, we got solid copper, we got this dilute nitric acid, then that forms some salt, that copper nitrate salt, and nitrogen monoxide gas, and water, liquid water. Okay, so they say 3 different experiments were conducted in which various reaction conditions were changed, and the data is tabulated below. Okay, so an experiment, well, before we look here at the table, so important sometimes what they do is underneath one of these chemical things over here, so under one of these species, what they do is they put a color. Okay, sometimes it'll be blue, sometimes pink, green, things like that. So in this case, they're saying that this aqueous solution thing over here, these copper ions are blue. Okay, so they're saying that this thing over here is blue. So we can think if we produce more of this thing over here, this copper nitrate, not like that, like this, if we produce more of this, it means we're going to see the reaction mixture is going to be more blue. Okay, so that blue is put there for a reason. Okay. So let's go back to the table. Let's have a look at this table that they've given us. So the 3 different experiments. So in experiment A, we're given this mass of copper here, this volume of the dilute nitric acid, this concentration of the acid, and then also the state of the copper, small pellets. All right, then experiment B, same mass, different volume, same concentration, and the state is large chunks. Then in C, the mass is 5,08, the volume is 0,05, and the concentration is 1,6, and we're using small pellets. Okay, so let's get into the questions. They say now we have to use data from experiment A. So very important, make sure we read up here. So don't just get going without reading up here. So we have to calculate the number of moles of copper using the values from experiment A. So we need the number of moles. So what happens for copper is we're given the mass. So what we can do is we can just use this formula where N is equal to the mass over the molar mass of copper. And if we do this, we know the mass of the copper is given in experiment A, 2,54. That's in grams. We got to make sure it's in grams. And we can find the molar mass of copper by looking at our periodic table in the formula sheet. So you'll see for copper, where's copper? There we go, 63,5. So that's the molar mass of copper. And if we put this in the calculator, we'll be getting 0,04 mole. Let's just double check that. That is indeed 0,04 mole. 0,04 mole. All right, not too bad for 2 marks. So that's the moles of copper. Now let's say calculate the number of moles of nitric acid, this HNO3. So again, we go and have a look, and very important, we're looking at experiment A, so everything in this row. So we're given a volume of nitric acid, and we're given a concentration. So remember, these brackets mean concentration, and also these are the units of concentration. So we're given a volume and a concentration. So we're given a V and a C, and we need to find N. So what we can do is we can just use this formula. So you can say C is equal to N over V. All right, but then that just means that N is equal to CV, and our concentration is 0,8, and it's moles per decimeter cubed, so that's the SI units we need, and luckily our volume's in decimeters cubed, so we don't need to convert. So what was that volume? 0,10, 0,10. Okay, and when we do that, we'll get that we get this many moles. 0,08 mole of nitric acid. Nitric acid, cool. Now it says we have to show that copper is in excess. All right, so whenever they ask this excess stuff, what we have to do is we need to compare, we need to look at 1. Okay, so let me go to our reaction. So to determine what's in excess, what we do is we look at the reactant side. So we're going to be looking at this side. All right. And essentially what we do is we look at one of these. So we either look at copper or we look at nitric acid and we say, okay, so if I have this much copper, how much of this will I need? All right, or vice versa. But let's say we're looking at copper. So if we say, okay, I have this much copper, that means I'll need this much to react perfectly. Okay, in this ratio that's given. All right, you will see how we apply it in a second, but this is just a thinking. So we say, okay, if I have this much, I'm going to need this much. All right, you can almost think of it a recipe. If you have a recipe that says if you have 2 eggs, you're going to need something like 200 ml of water. 200 ml of water. Okay, that's an L, cursive L. So it's kind of what's going on here. It's a ratio, right? It's a recipe. But what happens is, let's say now you have 3 eggs. So obviously you can see, because of the recipe, you know the number of eggs is in excess. And that's kind of what we're going to do here. We say, okay, if I have this much copper, how much nitric acid am I expected to have? And then we say, okay, do I have more or less? So if you have less than you'll need it, that means that the thing you started with has excess, is in excess. All right. We'll have a look at that. So if I lost you a bit there, let's just have a look here. Okay, so we're essentially what we're doing is we're comparing the mole ratio, like we look at one. So we have to choose which one we're looking for at. Okay, and then we compare with the other one. So again, sorry if you're a bit lost, but just stick with me here. Let's get cracking. Okay, so let's look at the mole ratio between copper and nitric acid. So from the balance equation. So from the balance equation, it's 3 to 8. So 3 here by copper and 8 over there. All right. But my actual mole ratio, so rather not my actual mole, the actual number of moles of copper I have is 0.04. Okay, now I need to figure out how many moles of nitric acid would I need from this ratio. Okay, so there are multiple different ways you can do it. Some people put X over here. For sure, you could do that. Let's roll with that X method. Okay, so essentially, you know what, I don't like this X method. Let me show you what I do. So what I do is I say, okay, so I have copper, right? I know I have copper. So let's get this 3 to a 1. So how do I get this 3 to a 1? I just say divide by 3. So that's 1. Then if I divided the left by 3, I have to divide the right by 3. So this is 8 over 3. I'm going to leave it as 8 over 3 because otherwise it's going to have some weird decimals and I don't want to round. Okay. Now I say, okay, what was my actual moles of copper? It was 0.04. Okay. So what I did is, to get from 1 to this number over here, what I did is I times by 0.04. So if I did that to the left here, I also have to do it to the right. So that will be 8 over 3 times 0.04. And what that gives me is, so I work down here, 8 over 3 times 0.04. So what I get here is 0.211. All right, that's what I get to 2 decimal places. Okay, so that's what I get over there. Now, we say, okay, so our recipe says if I have 0.04 of copper, I will need 0.11 of nitric acid. But if we look how much moles of nitric acid we have, right, we have 0.08. So do we have enough? No, we don't, right? Because we're short. Okay, we're about 0.03 short. All right. So you can say that therefore copper is in excess. Okay, so therefore copper is in excess. Okay, so a lot of working in there for 1 mark. So there are quicker ways you can do it, but I think they're more prone to making mistakes, these quicker ways. So I prefer doing it as sort of this longer way with the mole ratio. But there are quicker ways you could do it directly, but I think it's easier if you follow this process with the mole ratio. Okay, so I prefer to teach that way rather than some other methods that, for example, you'll see on the memo, which is essentially the same thing. It's just they do it really quick, which sometimes can be confusing for students. So I prefer this one. Okay, so hopefully I didn't lose anyone there, and hopefully helped you guys out with maybe this little step that we did over here. Showed you something cool. Okay, so here we go. Now it says, assuming that the reaction proceeds to completion, calculate the volume of this nitrogen monoxide gas that would be produced at STP. So we need to be calculating a volume of nitrogen monoxide. So let's have a look at our reaction over here. So we're trying to figure out what is the volume of this gas produced. So if you look at your formula sheet, we need to be thinking about what formulas we could use there. We don't know the concentration of this nitrogen monoxide, right? So we can't use C's N over V. So the formula we're going to need is probably this. N is equal to V over Vm. All right. The reason we can use this Vm is because we're at STP. All right, so we know what this Vm, it's a constant. It's on your formula sheet. It's 22,4 decimeter cubed. Okay, it's on the formula sheet. So we're looking for the volume. So if we know the moles, if we know N, then we're sorted. Then we can apply this equation because we know Vm as well. So let's see how we find the moles of nitrogen monoxide. All right, so we look at our balance equation and we're just going to use a mole ratio. Okay, pretty standard. We're trying to find out the number of moles of this. So we just use the number of moles of something we know. Okay, but very important here. All right, copper is in excess. So we can't use the mole ratio from copper to nitrogen monoxide, right? Because we have too much. We have too much copper. So we're limited by the nitric acid. We're limited by the nitric acid. So we can't, if copper is in excess, if you do the mole ratio, you're saying you're not taking into account our recipe, right? So let's say we had these 3 eggs, right, for copper. Let's say we had 3 eggs, okay? But say we had no water. Can we produce, I don't know what and all the different ingredients, could we produce a cake with that? Just 3 eggs. We couldn't, right? Because we need the water and all the other stuff. Okay. So you can't use the thing that's in excess. You have to use the thing that is limiting, which in this case was the nitrogen, not the nitrogen, the nitric acid. Okay, so we're going to have to use the moles of nitric acid. And what I've underlined here in red is the moles of nitric acid. We've already calculated that. Okay, so we have to use the 0.08 moles because this is what we actually have, right? We use the concentration we actually had and the volume we actually had. So now we know the moles that we actually have. I know I said actually have a lot there, okay? But it's important. So we don't use the 0.11 either, okay? Because this is ideally the ratio that we would use, right? That 2 eggs to 200 ml water. But we don't actually have this, right? We only have 0.08. So we have to use this part because this is limiting. Okay, hope you guys are with me there. So we apply our mole ratio. And we're using nitric acid. And we're trying to find nitrogen monoxide gas. Okay, so from our balance equation, you'll see that it's 8 to 2. The ratio is 8 to 2. And what I would recommend is, well, again, let's do this properly. So if I divide this whole thing by 8, I'll get that this is 1, 2, and then this is 2 over 8, which is the same as 1 over 4. Okay, you guys with me there? So divide by 8. All right, then I know that my moles of nitric acid from this equation that I've underlined is 0.08. So 0.08. So what I see is I had to times this line by 0.08. All right, and what you'll see there is if I say 1 over 4 times by 0.08, what I'll get is 0.08 is to 1 over 4 times 0.08. That gives me 0.02. All right. So obviously also what you could have done is you can just say, okay, well, to go from this 8 to that 2, I have to divide by 4. Okay. You could have just gone from this step directly. Say, okay, I take this, divide by 4, it gives me that. Okay, but again, if we're doing it the proper way, you can, if you're not sure, you can do the proper way from essentially first principles, doing all the steps. Okay, anyways, so here we have the moles of nitrogen monoxide. So that's what we needed up there. So we say N is equal to V over Vm. So our moles is 0.02. Our volume we're trying to find, and our molar volume at STP is given. All right, so if we multiply those two things, we get a volume of, how many decimal places do they want? Okay, I think the instruction sheet said 2 decimal places, but the memo is reporting it to 3. Let me just double check. There's no ways I said 3 decimal places in at the top, at the instruction sheet. I don't actually have it here. So I'm pretty sure it was 2 for this paper. I forget if the instructions are important. I don't know why the memo is reporting it to 3 places. I'm going to report it to 2. All right. So that's how it would be when it's rounded. And the units here are decimeter cubed. Okay, so there we go. Let's look at the next question. It says the no gas, nitrogen monoxide, was collected in a gas syringe. The volume of this gas produced in experiment A is plotted against time. So here's A, so it's plotted over here. And it says draw the curves that will be obtained for experiments B and C on the above axes. Label the 2 new curves clearly. Okay, so just like we labeled this one A, we're gonna have to label experiment B and C clearly. Okay, so we know that this volume, we actually know what this volume is. The volume over here that we just got was 0.48 decimeter cubed. Okay, but be careful, this is in centimeter cubed. So to go from decimeter cubed to centimeter cubed, what we do is we times by 1,000. So 0.48 times by 1,000 gives us 480. Okay, so this is 480. Let me double check. Why are we getting 480? Okay, memory was being a bit weird there, but essentially what we do is the volume, we take this 0.45 and we times by 1,000 and we get 450. Okay, so the volume here in centimeters cubed is 450 centimeters cubed for experiment A. So what we have to do is we need to determine the volumes of this nitrogen monoxide gas produced for these 2 experiments as well, B and C. Okay, so let's have a look at experiment B. So the mass of copper is the same. So we know the moles of copper will be the same. So for copper, the moles is exactly the same as the previous question, which we got in 311, which is 0.04. 0.04 mole. I'm not going to write the mole here, but, and then also for experiment, let me put here B. Okay, then also for experiment B, for the moles of nitrogen, sorry, this nitric acid, what we have is, now it's a bit different because we have a different volume. Okay, so we're going to have a different amount of moles. So if we do N is equal to C times V, what we do is we find that the number of moles is our concentration, 0.8, times by our volume, 0.05. So now it's actually going to be half what it was before. So we can find out that it is 0.04, 0.04 mole. Okay, so the moles are halved of nitric acid. Okay, and remember, so before we had the same amount of copper and copper was in excess, but now we have less nitric acid, less moles of nitric acid. So copper is definitely still in excess. So to work out the volume of nitrogen monoxide gas, we're definitely going to have to use the mole ratio with nitric acid again. So what we do is, again, we're going to say H, I should put this all in orange. Okay. And we'll use a different color for experiment C. But anyways, so we're using the mole ratio, HNO3, and we're trying to find the volume of nitrogen monoxide gas. Okay, nitrogen monoxide gas. So again, we do this. I'm going to go pretty quick. And the original ratio was 8 to 3. Wait, let me double check that. 8 to 2. So the ratio is 8 to 2. So if we have this 0.04, we divide by 4, so it's 0.01 mole of nitrogen monoxide. So again, it's just half of this. So the volume will be half. Okay, so half the volume of this 450, that's going to be 225. But if you look, we have 1 block, 2 block, 3 block, 4 blocks, right, to get to the 450. So half will be over here, this one over here in the middle. So we know we're going to produce this much volume of nitrogen monoxide gas. Okay, but we need to be a bit careful here. So we're producing half. We also need to check the rate of reaction, okay? So we need to decide, okay, is it going to be the exact same rate, but then it just goes over here, right? Or is our rate going to be different? Well, remember the gradient of this line determines our rate of reaction. Okay, so we need to think, how is the rate going to be different? All right, is the rate going to be same or less or more? Okay, so let's look at the conditions in experiment B. Okay, so we need to remember some of the conditions that affect rate of reaction. So there's 6. So the 3 easy ones to remember are temperature, pressure, and concentration. Okay, temperature, pressure, and concentration. And then the other 3 are state of division, nature of reactants, and catalyst. Okay, so they mention nothing about temperature, so we don't have to look at temperature. The concentrations between A and B are the same, all right? But what's the state of division of copper is now we're using large chunks, right? So we're going to have less surface area, so the rate will be less. So what will happen is your rate, the line will be less steep. Okay, so it'll be something like this. Okay, this is for experiment B. All right, so you'll see our gradient here. Let me use a different color for that. Our gradient, which represents the rate of reaction, is less steep than over here. Okay, because the rate is less because of the large chunks. Okay, so that's for experiment B. Now we need to check experiment C. So I'm going to erase this over here. Okay, now we're working with experiment C. So now our mass of copper has changed. All right, so if we look at copper, the moles of copper is N over M over M. So that's 5,08 over 63,5. And what happens is that gives us 5.08 divided by 63.5. That gives us 0,08. So obviously this is just double the number of moles of copper we had before because we doubled the mass. Okay, and then for nitric acid, we've got to check the number of moles. So if we check the number of moles, we use that N is equal to CV. So our concentration is now 1,6 and our volume is 0,05. So that gives us 0,08. No, let me double check that. 0,05. Yeah, that's right. 0,08 mole. Okay. So again, if copper was in excess before with 0,08, right. So let me say that. So copper was in excess when we had 0,04 mole. Now we have more copper, right? So before it was 0,04 mole of copper and 0,08 mole of nitric acid when we worked with this stuff over here. Okay, so it was 0,04 mole of copper and 0,08 mole of nitric acid, and still copper was in excess. But now we've doubled the mole of copper, the moles of copper, so copper still has to be in excess. So again, we're going to use this number of moles for, because this is limiting. So to determine the volume of nitrogen monoxide gas, we're going to have to use this number of moles of nitric acid. But we've already done that, right? So we've already done that. So we can save some space, right? Because if you see this line over here, we've already worked out that if I have 0,08 mole of nitric acid, that means I produce 0,02 mole of nitrogen monoxide, which then ends up with a volume of 0,45. Okay, so we're saving a bit of time here. You could do everything in the same steps, again, where you determine what's in excess and then the volume. But it's important to save time here, okay? Because I know a lot of people struggle with time for these exams. And yeah, we're going to have to save a bit of time here with that. Okay, so we know we're going to produce the same volume. Okay, so C is going to end up at the same point, the same volume. But now again, we need to double check the rates. We need to double check the rates. Okay, so let's see what's what's happening here. So the mass of copper is increased, okay? But remember, the 6 factors is concentration, temperature, and pressure. Okay, so it has nothing to do with mass. Okay, the mass of copper, a solid, does not change the concentration. So we're not increasing concentration of anything. So it doesn't affect the rate. All right, and we're using small pellets. Well, in A we also use small pellets, right? But the main factor here is the concentration. So remember, the brackets are concentration. So we've increased the concentration of nitric acid. So that means we must increase the rate of reaction must be greater, must also increase. All right. So that means a line is going to be steeper over here. So it's going to be steeper. We're going to be, well, that is a terrible line. So it's going to be steeper. We're going to reach equilibrium quicker, but at the same point, the same volume. Okay. We're going to get it at the same volume because we still only produce this amount of nitrogen monoxide. Okay. So this is experiment C. All right, so it'll be a higher rate of reaction. Okay. Okay, hope everyone's happy with that. I know this question is a bit weird. I mean, for example, this one was 1 mark and there was so much working. This one was 4 and there was so much working. But yeah, so don't let that throw you off, guys. If you have to trust yourself, trust your knowledge and your principles, and just take it step by step. Just be like, I know this, I know that, so this means that. Okay. So just take it step by step. Don't let the mark allocation throw you guys. Okay. I know it's helpful to look at these, but don't let it throw you off that you rob yourself of all these marks. Okay. Trust yourself. Trust your knowledge. Trust yourself in every little step. So try to commit to something, and if you believe it's right, go with your gut. Okay, that's what I'm trying to say there. So just a bit of advice, not related, well, I guess related to the exam. Okay. All right, now we have to say how an increase in concentration affects the rate of reaction in terms of collision theory. Okay, so this is just something you have to memorize. All right, but there's a bit of a formula to follow. So I don't mean a formula like C equals N times B. I mean a bit of a step process. Okay, a bit of a recipe we follow here. So we have to, essentially what we say is you make a general conclusion, then you say that there's more or less collisions, and then you say more or less effective collisions, and then you discuss the rate. Okay, so let me write that. So there'll be a general statement. Okay, then what you'll do is you'll say collisions. Okay, then you'll discuss collisions. So just collisions. Sorry, you know my spelling, collisions. Okay, so that's essentially step 1. Well, there's a step 0. But then step 1, you talk about collisions only, right, per unit time. So per unit time. So UT stands for unit time. Then step 2 is you say you discuss effective collisions. So effective collisions, all right, per unit time. Okay, per unit time again. That's really important. Then step 3 is you discuss the rate. All right, so you'll see in a second. But there's a bit of a recipe you follow for these questions. So if you're struggling to memorize everything, have a look at those recipes. It comes up, okay? It comes up a lot in chemistry. So let's have a look. So we're increasing the concentration. So how does that affect the rate of reaction in terms of collisions here? Okay, so what happens when we increase the concentration? This will be our step 0 that I was talking here. So if we increase the concentration, right? So that means there are more particles per unit volume. Per unit volume. Okay. So that's what concentration means, okay? So you have to be saying per unit volume. So you can't just say there's more particles, okay? Because when we added more particles of copper by increasing the mass, that didn't affect the rate. It's about concentration. So concentration is the particles per unit volume, right? So remember concentration N over V. So you have to say there's more particles per unit volume. This is important. Okay, so this is our general statement, all right? So we say we're discussing the effect of one of the variables, okay, one of the 6 factors. So there's more particles per unit volume, all right? So if there's more particles in a space, right, that means there's going to be more collisions. Okay, so we can rather say therefore. therefore more collisions, all right? More collisions per unit time, okay? We say per unit time because we're discussing rate, okay? So it doesn't matter if there's just more collisions if it takes longer, right? It's per unit time because of rate. You guys with me? So it doesn't matter if you, for example, it doesn't matter if you cover more distance on the way to Durban. It depends on how much distance you travel and the time in terms of speed, which is a rate. Okay, so we have to say per unit time. All right, so there's more collisions, but importantly, more per unit time. So now we're talking about collision theory. Collision theory is all about effective collisions. So now we have to say, okay, so if there's more collisions, right, that means more effective collisions, right? So effective collisions, there's three conditions. They sufficient kinetic energy, correct orientation, and I don't know if there's three or two. I forget. I think there's two. But anyways, so we have to now be saying there's more effective. So if there's more things colliding, then there has to be more effective collisions. All right, I'll be right back. Let me double check the conditions for effective collisions. Okay, we're back. So yeah, I was right. There are two things. So they have to collide. So a successful or effective collision, they have molecules or particles have to collide with the correct orientation and sufficient energy. Okay, and that energy is related to the activation energy. Okay, so if there's more collisions, obviously there's going to be more effective collisions. Okay, because not all collisions are effective collisions. So not all collisions will result in a, a effective collision. So a successful collision. Because some of them don't meet the conditions. Okay. All right. So that was a bit of a sidetrack, but anyways, more collisions per unit time. So that means there's more effective collisions. Effective collisions, what? Per unit time. Okay, really important because we're discussing rate. Per unit time. Okay, per unit time. And then very important, we're discussing rate. All right. So you need to be saying, therefore, the rate will increase. Okay, rate will increase. All right. So obviously, if there's more effective collisions per unit time, then the rate of reaction will increase. Okay. So hope everyone's happy over there. Let's move on. So they repeated the reaction for us over here. And they say some alternative methods of measuring the rate of reaction are given here. So here's one of them, and here's the second one. All right, so in the question 341, we have to state whether the pH of the mixture would increase, decrease, or stay the same as the reaction proceeds. Give a reason for your answer. Okay, so let's have a look. So if you're thinking pH, you need to be thinking of concentration of hydronium and the concentration of hydroxide ions. Okay, so, but it's not evident what, we don't see any of these two things, these concentrations here, okay? But let's have a look. This is an acid. This is nitric acid. So as the reaction proceeds, right, as the reaction proceeds, we are getting rid of this acid. Okay, so we are getting rid of these hydronium ions. So if you get rid of hydronium ions, it becomes less acidic, okay? And less acidic means that we have a higher pH, okay? Because acids have low pH. So if we're getting rid of the acid stuff, we must be getting a higher pH, okay? So we say that the pH will increase, okay? All right, increase. And I guess they want it in all caps, okay? So yeah, just make sure we write this in all caps. I'm too lazy, but I'll do it for the next one. All caps, okay? And we need to be giving a reason, okay? And it's because the concentration of our acid is decreasing. Or you could say the concentration of this, or there's a few different ways. So you could say that the concentration of our acid is decreasing. Concentration of acid is decreasing. So I'm short forming it there. So yeah, the concentration of the acid is decreasing. So that's why the pH will increase. Okay, then this one is an interesting one. State whether the percent transmission of light through the reaction mixture would increase, decrease, or stay the same as the reaction proceeds. Give a reason. So again, this is a bit of a weird one. You'd be thinking, whoa, like transmission of light. What's going on here? But again, remember, they put this here for a reason. We haven't used it yet, but it's there for a reason. So as the reaction proceeds, it's going to get more blue. All right. So here we assume that this is colorless, but then as the reaction proceeds, it gets more blue. Okay. So if we look at the percent transmission of light, all right, if something gets blue and this was colorless or see-through, obviously less light's going to be able to get through. Okay. So the transmission of light would decrease. Okay. Decrease. Okay, I'm not going to write in all caps. It's annoying. It takes more time. But anyways, decrease. So it's going to decrease. And the reason is the concentration of this thing is increasing. Okay, so you'll say that the concentration of that salt, that aqueous salt, that's copper NO2, sorry, NO3, 2, is increasing. All right, and so the solution becomes darker blue. All right, so it's becoming darker blue. Okay, so concentration, that's increasing, so the solution becomes darker blue. Okay, and obviously it becomes darker blue, that means less light going through, becomes darker. Darker blue, less light going through. I hope that rhymes. Okay, darker blue, less light going through. Okay, maybe if that comes up again in another exam, you can remember that rhyme and maybe that'll help you out. I'll doubt it, but who knows? Okay, so they give us the reaction again, and we have to define redox reaction. Okay, so this is just a memorization thing. Again, I do have on my website on the downloads page, I put all the definitions in a nice table format. So if you're struggling with definitions and trying to find them in the SAGs, and I know it's super annoying, I basically just have all those definitions in a nice little table format, and I've organized it by section as well. So if you're struggling with the electrodynamics definitions, you can just scroll down to the electrodynamics definitions. Okay, so that was a bit of a shameless plug. But anyways, define a redox reaction. It just involves transfer of electrons. So it's a reaction involves transfer of electrons. I'm not going to write the whole thing here, but yeah, transfer of electrons essentially is the reaction. So it involves transfer of electrons. Okay, identify the reducing agent in this reaction. Okay, so the reducing agent is the thing that is oxidized. Okay, but then what does oxidize mean? Okay, so we can use the mnemonic oil rig. All right, oxidation is loss, reduction is gain. So oxidation means loss of electrons. Okay, so we need to find something that loses electrons. So if you lose electrons, you become more positive. If you get rid of the negative, you get more positive. Okay, so we actually need to expand this aqueous thing over here. So what you'll see is this actually becomes copper 2+, all right? Because nitrate has a, where's nitrate? It has a valency of -1. Okay, so copper becomes copper 2+, and nitrate is minus over here. So that should be a 3, and that would be a 6. Okay, so yeah, but mostly what we're concerned about is just the valency of the copper over here. Okay, so copper is the reducing agent because it undergoes oxidation. All right, so it undergoes oxidation. It's oxidized. Because if something gets oxidized, it loses electrons. So because copper became more positive, because the charge here was 0, and now it's +2 or 2+, it is now, it's lost electrons. Okay, so copper is the reducing agent. All right, and it says identify and write down the ionic equation for the reduction half reaction. So refer to the table of standard electrode potentials. Okay, so let's break that down again. So they want the reduction half reaction. So from our mnemonic up there, reduction is gain. So we need to be looking at what gained electrons. All right, so if we split this over here, we'll see that this becomes H+, and this is NO3-. Okay, so with the NO3-, what happens? So obviously that we get some of this, but we also produce water, and NO2. So we need to be looking at the reduction is the thing that is gaining electrons. Okay, so we need to be looking at the thing that is gaining electrons. So obviously, if we were working with copper over here, we're going to have to be working with nitrate in the other reaction. So copper was the oxidation half. So something with nitrate is going to be our reduction half reaction. All right, so let's see what reaction involves nitrate. Okay, so let's just break this down actually a bit more. Okay, so essentially what we have is our full reaction expanded in essentially ionic form. Is we're going to have that 3 copper as a solid plus 8 hydrogen ions plus 8 nitrate ions forms 3 copper 2 plus ions plus 6 nitrate ions plus 2 nitrogen monoxide gas plus 4 H2O. All right, so essentially what's happening here is with the reduction half reaction, you'll see that 6 of these nitrates are over here. Okay, so essentially what we're left with is 2NO3 minus, and that's going to form is 2NO plus 4 H2O. Okay, obviously we can divide by a factor of 2 here, which I will do. NO3 to NO plus 2H2O. Okay, so I know there's a lot of weird shenanigans going over here. So essentially what we're trying to do is we're trying to find, okay, what am I looking for in this big table? Okay, the standard electrode potential table is a big thing. Okay, so if we look at it, we're trying to find something with nitrate. Okay, we're trying to find something with nitrate that forms nitrogen monoxide and water, but it's a reduction reaction. Okay, so it's going to be NO3 minus plus some electrons. Okay, we don't know how much electrons, but we know that they're going to react and then form nitrogen monoxide and water. Okay, we need to find that. Okay, so in the table, all right, let me pull up the table. Well, let me not pull up the table. So the table is, you'll see with the table, you should have it in front of you. Okay, so the table, the left-hand half is, they're all written as reduction. So all a gain of electrons. Okay, so what we do is we can just look in the left column only. Okay, because it's a reduction half reaction. Okay, so we look in the left-hand column, so that makes it a bit easier for us. Okay, so if we work from the top down, we're looking for nitrates. Okay, I'm going past hydrogen now in the middle. Still no nitrate. Still looking for nitrate. Okay. So nitrates between here, mercury and silver. And you'll see that this is the reduction half reaction. You just write it directly from that table. You'll see that the reduction half reaction is NO3 minus plus, I lost it. Okay, I'm with it. Plus 2H plus E minus gives us NO2 as a gas plus, we don't have to have state symbols here. Okay, and it's NO, sorry. Okay, you see the mistake I made. Okay, this is a good learning moment. Okay, so if you chose that first one like I said, okay, I made a mistake. So the reason we can't choose that one is because we produce NO2. But do we produce NO2 here? No, right? NO, no. Okay, so we can't actually use this one. Okay, but you'll see just right below it, I think it's 2 places. Yeah, 2 places below it between silver and bromine, right? You'll see that it's the actual one that we have, where it's this NO3 plus 4H plus E minus, okay, reacts to NO as a gas, but we don't need state symbols, plus 2H2O. Okay, so that is the reaction. All right, but very important, you'll see on the table it's written as a double arrow. You might be asking, why don't I write a double arrow? Okay, but if we look up here, do we have a double arrow up here? We don't, right? So it can only proceed in the forward. Okay, it can only proceed in the forward. That's why we just write the forward arrow. All right, that's a beautiful arrow. Okay. All right, so I hope I haven't lost you guys there, but I hope that breaking down this thinking, I know it was maybe not the best explanation, but I hope that it kind of put you in the right headspace to know what we were looking for. All right, cool. So let's now look at question 4. All right, so a lot of you look at this and you guys start panicking, but let's take it easy, okay? Let's just look at it step by step. All right, it's doable, guys. It's very doable. Just take it step by step. I know people get so lost in the chateliers and all these graphs, but take it easy. Deep breath, step by step. All right. So, sample of N2O4 gas is sealed in a container and heated. The N2O4 gas decomposes to nitrogen dioxide, NO2 gas. The reaction reaches equilibrium according to the following balance reaction. Okay, so we got double arrows. Okay, so we got dynamic equilibrium. Okay, so here's our reaction, and we're given that this. Okay, so you should memorize this. If it's delta H greater than 0, we know we have endothermic. All right, so the forward is endothermic. Okay, for the forward. Okay, the forward is endothermic. All right, so one thing I want to note here, normally what you guys will see sometimes in notes or textbooks is the forward reaction is always given by a solid line. Okay, so we'd always treat this as the forward, normally, in textbooks or notes. But very careful, N2O4 is produced with what? With the reverse reaction. Okay, so the solid line in this case is reverse. So I'm going to write here reverse. Okay, and then the dotted line is our forward. Okay, so obviously they say that this N2O4 is sealed in a container and heated. Okay, so that implies that we start with 0 NO2. And it's confirmed over here. So we start with 0 NO2, all right? So this graph is NO2. And we start with a concentration of this N2O4, where they say the sample. Okay, so some concentration. Okay, then we have the graphs of concentration. So obviously it reaches equilibrium somewhere here, okay? Because equilibrium is when the concentrations don't change anymore. All right, then there's some changes. So we're probably gonna be looking at the chateliers, maybe temperatures change. Because we're working with gases, the concentration / pressure could change. We discussed temperature. We can discuss, there's a lot of different stresses that could happen to our system. Okay, and we're probably going to have to identify volume changes, pressure changes, stuff like that, temperature changes. Okay, but right now we're not concerned with that. Okay, we can look at it, but we're not really concerned. Okay, let's have a look. So it says, how does the rate of the forward reaction compare to the rate of the reverse reaction at the following times?
Okay, so we got editor Brandon here again. So my explanations here were pretty poor. Okay, so I think I'm just going to fix it here in the post-production part. So the reason the rate of the forward is greater than the rate of the reverse is because we've initially put that N2O4 in. Okay, so because you put that in, the system's going to try to produce everything on the right. So the forward is going to be heavily favored. Okay, so the rate of the forward is going to be greater than the rate of the reverse until the system reaches equilibrium for the first time. Okay, and you'll see there at time 2, the system reaches equilibrium for the first time. And once the system reaches equilibrium, we know that the definition of equilibrium is when the rate of the forward is equal to the rate of the reverse. Okay, so the rate of the reverse reaction is equal to the rate of the forward reaction. Okay, so that's why in part question point 2 there, they're equal. And in point 1, the reason that the rate of the forward is higher than the rate of the reverse is because we're favoring the forward. Okay, we're favoring the forward reaction because we've put in the reactants on the left hand side. So that forward reaction is going to keep going and it's going to have a higher rate until we reach equilibrium for the first time. Okay, hopefully that is a better explanation.
Now, let's have a look. It says, as the reaction starts, the concentration of NO2 gas increases faster than the concentration of N2O4 decreases. Explain this observation. Okay, so let's have a look at this graph. So this is the concentration. Okay, and they're saying that NO2 increases faster than the N2O4 decreases. Okay, so you'll see N2O4 has a kind of gradual decrease, where NO2 has a very high increase. Okay, you see how this is increasing fast. Okay, so it says the concentration of this NO2 increases faster, okay, than the concentration of this thing decreases. Okay, remember, concentration is number of moles over volume. Okay, they're in the same container, so they have the same volume. Okay, but if we look at the number of moles, 1 mole of this N2O4 produces 2 moles of this NO2. Okay, so that's why the concentration of the NO2 increases faster, increases twice as fast. Okay, so for example, if you lose 1 mole of this, you'll gain 2 mole of that. Okay, so there it's related with that. Okay, so it's a mole ratio. Okay, and then obviously moles are related to concentration. So if you double the moles, you'll double the concentration. Okay. So that's literally what we write there. So we say, because of the mole ratio, so 1 mole, we can say that 1 mole of N2O4 produces 2 moles of NO2. Okay, we can literally just say that. All right. So let's look at the next question. So here, very important, we're given the rate versus time graphs. Okay. And again, let's have a look with, well, let's read the question. Let's read the query before we jump ahead. Okay, so it says at times 3, some NO2 gas was added to the container. Complete the graph below from T3 to T4 to show the effect of this change on the rates of the forward and reverse reactions. Okay, so we're looking at rate. Okay, but we need to think about what was the dotted line and what was the solid line. Okay, because remember it's not always the forward and reverse. There was some weird stuff going on. Okay, so remember this N2O4 was the reverse and the NO2 was the forward. Okay, so that's initially what was going on over there. Okay, and we know initially which one was higher, right? We started with this and we want to produce it. We had 0 of this. Okay, so Le Chatelier says we're going to favor the forward to produce more of this. So the forward was initially favored. But let's have a look here. So in this graph, you'll see that the forward was favored. The forward has a higher rate of reaction. Okay, so the solid line here is forward and the dotted is reverse. I know it's confusing, guys, because over here the solid was the reverse. Okay, so you have to keep a keen eye on all of these things. Okay, so I know it's a bit frustrating. I don't think they intentionally try to trick you here. You just got to be a bit careful. Okay, but let's have a look. Some NO2 gas was added to the container. Okay, so we're adding this, more of this. Okay, so we know from Le Chatelier's that the rate of the reverse will then increase. Okay, the rate of the reverse will increase. Okay, but the rate of the reverse will increase and then it will mellow out to something, a higher rate. Okay, but then also the forward has to increase. So the forward should be a solid line. Let me put the forward in orange. So the forward has to increase to go and meet at this new equilibrium. So actually, this should be a dotted line. Okay, this should be a dotted line like such. Okay, I know my drawing, I apologize, not the best. And yeah, so this would be it. So obviously we actually have to complete this graph up until T4. So something like that. Okay, to T4. So what's important here is that the rate of the reverse is the only thing that's increasing. Okay, because we're increasing the concentration of this, which means we'll favor the reverse. Okay, because of Le Chatelier's. So the rate of the forward, which is our solid line, is going to increase to meet the rate of the reverse that increase. Okay, so the memo here says that the rate of the reverse increases at T3, so the reverse is this blue. So the reverse increases because we're trying to balance the stress where we increase the concentration of the products. We're going to try increase the reaction of the reactants. So we're going to have to favor the reverse. The reverse is favored. Okay, so it increases. And then what happens is to now meet at this new point over here, the forward will then increase to meet this reverse. And equilibrium is going to be reestablished. And equilibrium, we know equilibrium when the rate of the forward and the reverse are equal. So you'll see here they're both equal, the same value. And it's at a higher. Okay, it will be at a higher, the rate will be at a higher point than before. Okay, so we've got that going for us. Now, question 4.4. So Sharik incorrectly says that the change at T4 is an increase in volume of the container. So we're looking here at T4. Here's T4. So state, do not redraw the graph, how the graph of concentration versus time on page 14. So page 14 is what I've put up here for us. That graph over here, I've repeated page 14 for us. And it says how would differ if the volume of the container had increased at T4. Okay, so important here. So Sharik incorrectly says that T4, oh yeah, there was an increase in volume. But Sharik is wrong. Okay, but we have to say, okay, if Sharik was right, how would the graph differ if the volume of the container was increased at T4? So again, I know a lot of weird wording here, and I know I'm maybe not explaining it the best, but we need to say how this graph would differ if the volume of the container had been increased at T4. Okay, so if you increase the volume, so volume is inversely proportional to pressure. So what that means is if you increase the volume increases, that means pressure will decrease. And if pressure decreases, pressure is one of the factors that affects our rate of reaction. So if our pressure decreases, right, that means that our rate of reaction will drop, okay? But also in terms of our pressure decrease, we need to look at Le Chatelier's. Okay, so if our pressure decreases, we're going to try to counteract that stress by increasing the pressure. Okay, so when we're trying to increase pressure, we look at the gas molecules. Okay, so this N2O4 only has one gas molecule, whereas this NO2, the forward, produces two. Okay, so because we're decreasing the pressure, that's our stress. What we're going to try to do is we're going to try and increase the pressure. And to increase the pressure, we have to favor the forward. So the forward is going to be favored. Okay, so that's important, but also very important, if there's a drop in pressure, there's an instantaneous drop in pressure. Both of these graphs would have an instantaneous drop. So there, let me put this as a dotted, and let me change the colors here. Okay, so both of them would experience, and so again, we don't have to redraw, do not redraw, we're just explaining. So what would happen is there would be an instantaneous drop on both of these guys. Okay, because it's concentration. So if you lower the pressure, for gas, pressure and concentration are essentially the same thing. So if you drop the volume, we're dropping the pressure, which is dropping the concentration. Okay, so they will both see an instantaneous drop. Okay, but we know that the forward is favored. Okay, and the forward is producing NO2. Okay, so the production of NO2 is favored, right? So this bottom dotted one is NO2. Okay, so then eventually the concentration of NO2 would increase, okay, and reach a new point over here. And the concentration of this N2O4 would decrease. Okay, so it will actually come to a lower value over here. But remember, it will eventually reach equilibrium, so it'll become constant. Okay, so it would look like this. So we need to be putting this into words. Okay, and essentially, I'd explained a lot here. I explained a lot, okay? So it's just there was a lot of thinking behind all of this, okay? But essentially what we say here is it's just both concentrations would decrease sharply. So that's all you need to say. Both concentrations would decrease sharply. Decrease sharply. Okay, that's all you have to say over here. Okay, but I think it was important that we looked at all the thinking behind it. Okay, so it will be helpful in general. It's helpful to know. Okay, and here what we have to do is, like I say, explain your answer to this previous question with reference to a suitable formula from the data sheet. Okay, so we need to show that both concentrations would decrease. Okay, so if we look at our formula for concentration on the formula sheet, we have C is equal to N over V. Okay, so what's happening is we're increasing the volume. Okay, so if the volume had been increased, what would happen? So if we increase this, right? So if you say 5 divided by 10 and you increase that to 5 over 20, obviously the concentration will drop. Okay, because concentration is inversely proportional to volume. All right, just like pressure is inversely proportional to volume. Okay, so yeah, okay, so essentially you just say this. Okay, so if the volume increases, then your concentration must decrease. Then your concentration decreases. Okay, so I know there's a lot going on there, and I did definitely overcomplicate it, but I hope that you followed along with those explanations. Alrighty, so let's continue. So it says here that the actual change at T4 was an increase in temperature of the equilibrium mixture. So now we have to use Le Chatelier's principle to explain the observations on the graph on page 14. So here's the graph again that I've repeated. It's the page 14 graph. Okay. So again, with Le Chatelier's, there is a formula or a recipe. Okay. So we have to say, we start off with step 0. And we say, in order to relieve the stress rather. So in order to relieve the stress, right? We start with this step, to relieve the stress. Okay. Then what we do is we say, which reaction is favored? Okay. So we have to answer which one is favored. And then we have to say, why is it favored? Okay, and then after we say why it's favored, we make a conclusion. Okay, we make a conclusion that's relevant to the problem. Okay, so let's have a look. So we start off by saying, in order to relieve the stress, all right, so in order to relieve the stress, and now we need to think, okay? So we've increased the temperature, all right? And we know that the forward is endo. So if we increase the forward reaction, if we increase the temperature, the forward reaction would be increased, okay? Because endothermic absorbs energy. So if you increase the temperature, we're going to try to counteract that by absorbing energy, okay? So in order to relieve the stress, the forward is favored. Okay, so now we're on step 1 over there. Forward is favored. The forward reaction is favored. Okay, now we're on step 2. Why is the forward reaction? Okay, well, we just said. Okay, so the reason it's favored is we can cross out that full stop and we can say because, right? It's favored because it is endothermic. The forward reaction is endothermic. All right, and then our conclusion, right, is here they're saying we have to explain the observations on the graph. And this is a graph of concentration. Okay, So what's happening is here, you'll see that this is our forward and this is our reverse, and we're looking here at T4. Okay, so we can say that while the forward is favored, so therefore, let me write, therefore the concentration of NO2, that should be square, therefore concentration of NO2 increases, and the concentration of N2O4 decreases. Okay, so that's what we have over there, and you can see how we have followed this recipe. Okay, and just be careful, the conclusion is relevant to the question. Okay, so if they asked about rate of reactions, if we had a graph of rate, you might have to be, you have to be discussing rate over there. Okay, so it changes depending on the question, the conclusion part. Okay, hope everyone is happy with that. So now it says at T5, a catalyst was added. So state and explain the effect of this on the equilibrium concentrations of NO2 and N2O4. Okay, so we're asking about equilibrium concentrations. Okay, so we know catalyst increases the rate of reaction. Okay, but what it does, it increases the rate of the reaction equally. So the rate of the forward and the rate of the reverse increase equally. So there's actually no change in the equilibrium concentrations, and that's what we need to say. Okay, so explain the effect of this in the equilibrium concentrations. We say the concentration remains constant. Okay, we can also see that on the graph. So the concentration remains constant. Okay, and we need to explain that. So we stated what happens, and now we need to explain. Okay, and it's because the catalyst increases the rate of the forward and reverse equally. Okay, so the adding the catalyst, or let's rather say adding the catalyst. So adding a catalyst of the catalyst increases the rate of the forward and reverse reactions equally. Alrighty, cool. Let's move on. So one thing, okay, obviously do not do this in your exam. Okay, I'm doing it because I'm lazy. Okay, and yeah, to save time. All right, 4.7. Now it says N2O4 gas was pumped into the container until the concentration was that amount. And it says the container was then sealed and heated to 100 degrees. At equilibrium, 20.7% of the N2O4 gas had decomposed to NO2 gas. The reaction is rewritten below. And there's a reaction that says write the expression for the equilibrium constant Kc for this reaction. Okay, so what you guys, some alarm bells that should be ringing is we're probably going to have to do a rice table. Okay. The reason it's looking like a rice table is firstly they ask Kc, and they start talking about at equilibrium. They're giving, they're saying what's happening at equilibrium. There's some change at equilibrium, so that's what the C stands for, change. Okay, so there's some change that's happened. Okay, so we start with an initial. Okay, well this is a concentration. So we start with an initial amount of moles. We're going to have to convert this to moles, but we start with an initial amount of moles, and what we have to do is then find out the change and what happens at equilibrium. Okay, but for now we just need to write the expression for Kc. So I'm going to write it down here. So it's just the ratio of the products. All right, and careful, that thing goes up there when we do Kc. Ratio of the concentration of the products over the ratio of the reactants. Okay, so remember, pure solids and liquids have a concentration of 1. Okay, so this is for solids and liquids. Okay, they don't have concentration. I'll change in concentration essentially. Okay, so that's just, we don't need it now. That's just a little sidetrack. Okay, so here's the same information, but the next question says we actually need to calculate the equilibrium constant, Kc, for the reaction at 100 degrees Celsius, which was given that condition over there. Okay, so we are given the, yeah, well, let's just see. So we're given the concentration. So let's just look at this. So the concentration of this is the initial concentration. Okay, so it's not this. All right, so this is not 0.46, okay? Because remember, these concentrations are at equilibrium. All right, so remember, it's called the equilibrium constant. So we don't use the initial concentrations for this. Okay. But let's have a look at this. Okay, so what we can do is you can actually also do, we're not going to have to convert this to moles because you can also do the Rice table in terms of concentration. Okay, if everything's in concentrations. So, but let's get into it. Let's do this Rice table. Okay, so we write R, I, C, and E. Okay, so our reaction is N2O4 is in dynamic equilibrium producing NO2 to NO2. All right, so here for reaction, we put the mole ratio. Okay, so 1:2, that's for our reaction. And then initially we had this amount of, well, this concentration. Okay, so earlier I misspoke. You can do a Rice table in terms of a mole basis, but you can also do it in terms of an equilibrium basis, but it needs to be, you need to be consistent. Okay, so if you're doing a Rice table, on the mole basis, everything here needs to be moles. So initial moles, change in moles, and at equilibrium, the moles. But then what you're going to do is you're obviously going to have to work out the equilibrium concentration because we're going to need that for Kc. Okay, because remember, these are concentrations, equilibrium concentrations. Okay, so we're going to have to do that. Okay, but that's if you do it on a mole basis, but you can also do it on a concentration basis. So all of these would just be essentially concentrations. So if they're all concentrations, then we're sorted. Okay, they didn't give us any moles, they gave us concentrations. Okay, hope I didn't confuse anyone there. So we know we initially started with 0.46 mole per decimeter cube. So this was our initial concentration. And they didn't tell us anything about NO2. They didn't say we started with any NO2, so we assume we started with 0. Okay, they do this often, where they just say that N2O4 gas was pumped into the container. So if they don't mention about there being an initial NO2, don't put it there. Sometimes they do give you an initial NO2 or an initial concentration of something's on the product side, then you put it in. But here, they didn't give us, so we put 0. Okay. Then, very important. So at equilibrium, 20.7% of the N2O4 gas had decomposed. Okay. So 20.7% of this had decomposed. Okay. So that means we lost 20.7% and that it was converted to the NO2 gas. So what we do is we know our change is going to be 20.7%. All right, so you could also write it like this. Let me rather do this. Let me do this on the side. So what we're going to do is 20.7% of this 0.46, this concentration. So that will be how much was decomposed or lost or our change. Okay, if we put this in the calculator, we get this value over here, 0.9522. There should be a 0 here. Okay. 0, let me neaten this up a bit. 0.9. And a comma there. Okay. So the reason I put a negative there is because it's being decomposed. Okay, it's being decomposed. All right. So what we do now is we take this difference. So this equilibrium over here is essentially when you take the difference between the initial and the change. All right, that makes sense. So if we started with 0.46 and we lost that amount there, we just subtract those to find out what we're left with. So when we put that in the calculator, we get this. Okay. I recommend working with all these decimal places because you don't want to round and then lose some marks. Okay, so what we need to do now is we know that if we take using the mole ratio, right? Now what we do is on this change step, what we do is we use this mole ratio. Okay, so if we lost this much, right? So remember we looked at the mole ratio concentration, we will gain twice as much of this NO2. Okay, remember we discussed it earlier in the question, and it's because of the mole ratio. 1 mole of this N2O4 produces 2 moles of NO2. So if you lose this amount of concentration, you'll gain double this on the other side. So that's literally what we do is we take that answer and we double it. Okay, and we get this 19044. Okay, and remember we're producing, so we say plus. So then at equilibrium, our equilibrium concentration is 19044. Okay, so we're not quite done because we want the equilibrium constant. So we use our KC from the previous page. Okay, I'm just going to rewrite it over here for us. And we have this. And now what we do is we just substitute in these values. Okay, so this over here is for NO2, okay, because it's in this column. So we say 0,19044. And please don't forget to square this now. Okay, don't forget that square. Don't come all this way just to not square. All right. Then at the bottom, we have this 478. Okay, and when we do that in the calculator, what are we getting? So 19044 square over 0.36478. That gives us 0,099. Okay, let's round that to 2 decimal places. Let's put the approximate sign, which is 0,1. Okay, so you could have also just wrote, you could just say that this thing is equal to 0,01 and just round it directly. I think this would be better. All right, so that was question 4. Now we're moving over to acids and bases. So our first thing we're given here is 3 acid solutions. So we're given solution A is 0,4 moles per decimeter cubed of H2SO3, which is sulfurous acid. Okay, sulfurous acid is considered a weak acid. Okay, so there's a bit of theory memorization going on there. Sulfurous acid is a weak acid. Okay, so it's sulfurous because this is SO3 and this is SO4. Okay, so the difference between sulfate and sulfite. Okay, so SO4 is sulfate and SO3 is sulfite. So that's why that's sulfurous. Okay, then solution B is the same concentration, that's 0,4, but of sulfuric acid, a strong acid. Then solution C is 4 mole per decimeter cubed of sulfurous acid, a weak acid. Okay, so I know I'm being very specific there, but it's important. So you see how just in this information, there's so much to unpack there. Okay, so that's the thing with chemistry. You always got to keep your eyes open, as I'm sure you've seen in this paper. Okay, so acid, pretty easy, is just a proton donor. So it just donates protons. Okay, proton donor. Then we have to name this acid H2SO3. Again, this is just a bit of studying. So this is sulfurous acid, sulfurous. Okay, sulfurous acid. You can also spell it with see they allow a pH. Okay, instead of that H, sulfurous. Okay, define a weak acid. So weak acids ionize partially. Okay, so acid that only ionizes partially. So I'm not going to put the full thing over here, but it ionizes partially in an aqueous solution. Aqueous solution. Okay, so those were essentially 2 definitions and 1 memorization thing. Okay, so don't let those cost you more, because I mean, what's this paper out of? 150, 3 divided by 150. So this is essentially 2%. You know, just from memorization, 2%. So don't let that cost you. Okay. So I know it's annoying. I also hate memorization, but again, I do have that definition document to help you. But yeah, it's also important to know your weak acids and bases. And yeah, also what I do have a document with weak acids and bases that explain, well, not explains them, but lists them. I'll also make sure to put that on my downloads page. Okay, so a little note for me, I will also put that so you have that in a table format. And I'll also have it with all the polyatomic ions. Okay, so I need to put that on my downloads page. Okay, so that's a bit of a note for me. But anyways, here are the acids again. And it says, what specific property of the solution does pH measure? Okay, so you can literally just say the concentration of hydronium. You can literally just write that. That just is a concentration of hydronium ions. Okay, so that's what pH measures. Okay, and now which solution will have the highest pH? Okay, so which one will have the highest? Well, so the highest. Okay, very important here. Highest in bold. So the highest pH will be the weakest acid. Okay, because if you look at the scale of pH, it's 1 to 14. So on the side of 0, you have strong acids, and the side of 14, you'll have strong bases. Okay, so 14 is higher than 0. Okay, so the higher the pH, the stronger, more basic something is. Okay, so if the highest pH will be the weakest acid. Okay, and that will be solution A. Okay, because it has this lowest concentration and it's sulfurous. This one is sulfurous as well, but a higher concentration. Okay, so solution A is the weakest acid, so it will have the highest pH. Okay, so let's see what Maya says. Maya says that C is the strongest acid solution. Correct Maya's statement. So there's two things you can say here. So no, C is not the strongest acid solution. B is the strongest acid solution. So no, she's wrong. So B is strongest. Okay. Another way to correct this is you could say, so this is option 1. You only need one of these. Option 2 is you can say, well, no, actually C is the most concentrated. So she was half right. She just, I guess, misspoke there. Okay. C is the most concentrated acid solution. Concentrated. What am I writing here? Concentrated. Okay, we know my spelling. Okay, C is the most concentrated. So one of those two options. All right, next question. So the polyatomic ion of those two things are given over there. So that's the first deprotonation of phosphoric acid. And then that thing over there is of some carbonate acid. I don't know the name of that one. But anyways, they can act as either acids or bases. So what is the term used to describe a substance that can act as either an acid or a base? Okay, so there's three things we could say here. I like this one. This is the one I like to remember. For me, it's the easiest one. So it's an ampholyte. Okay, so it's kind of like an electrolyte, but ampho is probably just means multiple forms or something like that as a prefix. Okay, if you're looking at the root of the word, if you're interested in linguistics and lexis. But so the word here is ampholyte. I prefer that. You could also say amphoprotic or amphiprotic. Amphiprotic, so careful with spelling. You could also say that it's amphoteric. Amphoteric. So these all mean the same things. Okay, as I said, I prefer ampholyte. Cool. And now we're given this reaction below. We have to label each substance as either an acid or base, and then link the conjugate acid-base pairs. Okay, so let's have a look. Remember, an acid is a proton donor. Proton donor. Okay, so let's see what donates a proton. So if something donates a proton, it's going to become less positive, okay, or more negative. And you'll see that this thing donates this H. All right, so it donates that H, which is just a proton, and it donates it, and then this thing, you see how this thing becomes more negative. Okay, so proton donor, you lose a proton, so you become more negative. So this is an acid. And then this is a base because it's a proton acceptor. You see how we got an extra H over there? So it's an accepted it, right? So that means that this over here is an acid, conjugate acid, and this is conjugate base. Okay, so to link these, this is the base and conjugate acid, and then this is the acid and conjugate base over there. Okay. So again, just trust yourself. A bit of a weird question. It's not even that weird. It's just, yeah, it's a lot of chemistry questions are weird, but just trust yourself. Trust the basics. Okay. Just, you see how we just literally looked at the definition and we could determine what was cracking over there. Okay. Let's have a look. So they say ammonium fluoride, that thing over there is a salt. When ammonium fluoride is dissolved in water, it dissociates into ammonium ions and fluoride ions. These ions both undergo hydrolysis reactions. Okay, so hydrolysis is just a reaction between an ion from a salt with water. Okay, so a reaction of an ion from a salt with water. So what we have to do is we have to write the hydrolysis reaction for here. So obviously we know we have NH4 plus, and it's going to react with water, and it's going to produce something. Okay, so it's a double arrow here for the hydrolysis reaction. And what I like to do here is, these can be a bit interesting, but essentially I have a look here. Okay, and I see, okay, this is a plus. So I'm going to need a plus on the other side. And to get the plus on the other side, what I'm going to do is I'm going to have hydronium. Okay, so you see how that's a plus, this is a plus. Okay, and I said, okay, if I got an hydronium there, that means that one of these H's went over there. Okay, so what I'm left with is NH3 plus. Okay, so it doesn't have a charge anymore up here. Let me put a square on there. It doesn't have a charge anymore because it had a positive charge, donated a proton. Okay, so you can see in this reaction that this ammonium is acting as an acid, okay, because it's donating a proton. Okay, now let's look at the fluoride ion with water, a hydrolysis reaction. So again, double arrow, because it's a hydrolysis reaction. And again, let me use a different color. So I know I have a negative ion here, so now I'm going to have a negative ion, hydroxide. Okay, and what happens is, to get a hydroxide here, I have to lose one of these H's. What happens is I get HF plus OH minus, and then it's balanced. Okay, so I hope everyone's with me there. So those are our hydrolysis reactions. Okay, so now we're given this things over here. We're given 25 degrees, the Ka. So Ka is the dissociation constant for the acid. Okay, so Ka is dissociation constant for the acid. Okay, and Kb is the ionization constant for the base. Okay. All right, so essentially what it says is it's an indication of how strongly the acid will dissociate or the base will dissociate for Kb. Okay, so we can determine the strength of acids using those constant dissociation constants, Ka for acid and Kb for base. All right, so we have to make use of the information to predict whether an ammonium fluoride solution will be acidic, basic, or neutral at 25 degrees. Okay, so ammonium fluoride is NH, so not NH4, NH4 here, F. Okay, so that's ammonium fluoride. They gave it to us up here. All right, so we need to see what is happening over here. So the acid dissociation constant for HF is 6,8 times 10 to the negative 4. Okay, but remember for this HF, right, we got HF from here. Okay, but we need to write it the other way because they're giving us the dissociation constant for HF. So that's when HF goes this way. Okay, so if we write HF plus OH, that reacts to form this way. What did it give? It gave us the fluoride ion plus water. Okay, so that was the dissociation That's our Ka for HF. Okay. Now, if we do the Kb for NH3, NH3 is here, but again, we're writing it as if this is dissociating into the left thing. Okay, because it's the Kb for NH3. Okay. So again, from that previous slide, we have NH3 plus, what was it, a hydronium. NH3 plus an hydronium, and that will give us NH4. Sorry, NH4 at the bottom with a plus H2O. All right. Sorry, I was running out a bit of space there. Okay, but anyways, which one is higher between these ones? Ka or Kb? All right. So because this is to a smaller power, -4, this is bigger. Okay, so the Ka of this is bigger. So essentially what that says is HF is more likely to go towards the right. So it's more likely to dissociate to the right. So you see how we get less of this, essentially. Okay, so we'll have less of this. Okay, so, and that means we'll have more of these hydronium. So if you have more hydronium, you're going to be acidic. Okay, and again, we've seen time and time again in this paper how you have to break down and manipulate things to see what's going on. Okay, you really got to do it in the chemistry paper. All right, so I hope everyone's following me there. All right, now they say which of Ka for NH4 or Kb for F minus will be the larger value at 25 degrees Celsius. Okay, now they're going back, and now there's some weird stuff going on there. Okay, so let's see if I could get rid of this and that. Okay, let me fix that H for us. Okay, now we have to do the opposite way. Now we're talking about this way. All right, let me use a different color. Because they're saying the Ka for NH4. So they're saying, okay, how badly does this thing want to dissociate that way? And how badly does this fluoride ion want to dissociate? Okay, but we know that this HF was more likely to dissociate. So you see how it wants to go to the right. Okay, so it's happy to go to the right. So this thing doesn't really want to go left. Okay, so you see F doesn't want to go left. Okay, so it doesn't really want to dissociate. Okay, so if we look over here, this F doesn't really want to go that way. Okay, because if we look here, the HF really wants to go to the right. Okay, so you see how this thing is almost blocking it. Okay, so that means this Kb value will be very low. Okay, it'll be a very weak base. It doesn't want to go this way. It's more likely to go this way. Okay, so which one will be higher? The larger value. So Ka, the Ka for ammonium will be higher. Okay. Also, what you could do is you could literally just look at the inverse of these ones. Okay. So because this HF was the higher one before, it is now going to be lower. Okay, so the inverse. So this, let me use colors here. So this Ka for HF was over here. So for HF, okay? And now what we're doing is we're working with the Ka for, well, actually this corresponds, let me remove this as well. Okay, so this Ka for HF corresponds now for this Kb, right? Because now we're looking at F minus. Okay, so you see what I've underlined here, they correlate to each other. Okay, so what you could do is you could just inverse this and inverse this similarly, okay, because this will correlate to this. Okay, so before we were given this, and we're given this now. So if this one was higher before, then now this one will be lower. Okay, so that's what I mean, that kind of inverse relation there. Okay, so that's what will happen there. So that's why this was the right answer for this one. Okay, so again, a lot going on over there. And now we have to explain our answer in 5.3.3a. Okay, so this one. And refer to the relative extent of ionization in the true hydrolysis reactions. Okay, so if we have a look at this, so let me neaten this up. So what's happening here is we know that HF is happy to dissociate. Okay, so it's happy to dissociate. All right, so what happens there is you're getting rid of these hydroxide ions. Okay, so the concentration of these hydroxide ions are decreasing. Okay, so and the reason is that if we look at these hydrolysis reactions, okay, so that plus should still be. If we look at these hydrolysis reactions, all right, so what's happening here is which one ionizes more? Okay, NH4 ionizes more, okay, compared to this fluoride ion. So the ammonium ionizes more than the fluoride. Okay, so the reason we know that is given by these Ka values. Yeah, it's given by these Kas. All right, so the memo wants you to look at these. Okay, I'm going to explain it using what we did up here, because this is what we used up here for A. We used these equations. Okay, so what I'd say is what I've done over here, because this HF is more likely to dissociate, right? Because it has a higher Ka. Then you're going to be getting rid of these OH ions. Okay, so that would be my reasoning. Okay, so I would say that HF ionizes more than NH3. Okay, so I would say that. And then I would say, okay, well, that means that the concentration of ammonium ions is going to be greater than a hydroxide. Okay, this should be a plus. And yeah, we have to make this conclusion because it's about pH. Okay, so that's what I would say. But what the memo does is they get the same conclusion, all right, the same therefore step. But what they do is they look at these reactions. Okay, and they say that NH4 ionizes more than F, the fluoride ions. Okay, so if this thing ionizes more, you'll be getting more of these hydroniums. But if this doesn't really ionize, you're not really going to be getting too much of these. Okay, so then H3O concentration will still be higher than hydroxide. Okay, and I keep forgetting this plus. Okay, so essentially what they say is that the ammonium ion ionizes more. Let's drop that wrong. More than the fluoride ions. Okay, I think they will accept both though. So I would have stuck with the one I had before. Okay, I hope everyone's with me. All right, this paper's been a bit all over the place, but I hope everyone is with me and I hope some of it has made sense. Okay, please let me know if you are completely lost in this paper. If you need help, I can re-explain, I can redo some sections. Please let me know. Okay, but I hope it has been helpful as always. Anyways, let's move on. So a standard solution of sodium carbonate of this concentration, okay, was prepared in a volumetric flask, and that volume of this solution was transferred into a conical flask. The concentration of HBr, bromic acid, I think it's called bromic acid, was then determined by titration. Okay, so the concentration of this, okay, this HBr. Okay, so they say write down a balance equation for the reaction of the sodium carbonate with HBr. State symbols are not required. Okay, so we have Na2CO3 plus HBr. Okay, let me make that R a bit bigger. So what we need to know is what type of reaction this is. Okay, so this type of reaction is a metal carbonate with an acid. So you need to know the different conditions. So you need to know what happens when it's an acid and active metal, acid and a metal oxide, acid and a metal hydroxide, acid and a metal carbonate, and an acid and a metal hydrogen carbonate. Okay, you got to know all the different reaction conditions on what's produced. Just like for combustion, you have to know that it's a organic compound, a hydrocarbon, plus oxygen produces CO2 and water. So just like that, you have to know what happens here. Okay, so here we have a metal carbonate, okay, because CO3 is a carbonate, okay, and sodium is a metal, okay, and HBr is an acid. All right, so when you have a metal carbonate and acid, what we produce is a salt, right? So that'll be an sodium bromide salt, okay? And the reason I know it's NaBr is because if I look at the valencies, they're both 1, and then what I do is I use the cross rule like this. Okay, so it's NaBr, and we produce a salt plus carbon dioxide plus water. Okay, so we have this first. All right, so you need to memorize that this is what we produce. We produce a salt, CO2, carbon dioxide, and water. Okay, when we have this type of reaction, when we have a metal carbonate and an acid. All right, but we're not done because we need to balance this now. All right, so let's see. So Br is balanced. The bromines are currently balanced. Let's sort out the sodiums. Okay, we have 2 here, we have 1 there. Okay, so let's balance the sodiums. Now we have 2 Brs there. Let's balance them here. So we need 2 there. And let's see now. So our hydrogens here on the left, we have 2. There we have 2. Our oxygens here on the left, we have 3. And here we have 2 plus 1 is 3. So we are balanced. Yep, cool. We're balanced. Okay. So now, question 542. It says the sodium carbonate solution in the conical flask was neutralized by that volume of HBr solution. Calculate the concentration of the HBr solution. Work to 4 decimal places at each step of the calculation. Okay, so this is a titration. Okay, so we're going to have to eventually get a mole ratio. So we need to be working with a mole ratio. Okay, so over here, we're given the volume, and we have to calculate the concentration of this HBr solution. Okay, so we're going to be using C is equal to N over V. Okay, so we're given the volume, and we're trying to find concentration. So we need to find moles. Okay, this is our goal. Okay, I'll put here G for goal. So that's a terrible G, but I hope you guys can see. All right, so again, not the right, but anyways, so we need to find the number of moles. And the way we do that is using a mole ratio. So first we need to find something we know. So we know the concentration of, this is the concentration for the sodium carbonate, and we know that the volume of this thing we have. So let's work out the number of moles. Okay, so we're working out the number of moles of Na2CO3. So I recommend actually writing this in your exam, so you don't get lost about which moles are which. So if you just have N is equal to something here and N is equal to something there, you're like, okay, which one is my sodium, which is my bromine acid, right? So yeah, that's why I recommend having these little heading things at the top. But essentially what we do is we have the concentration and the volume. So what we say is N is equal to Cb. All right, and we have our concentration at 0.12, and just be careful, don't forget this. We have to work to 4 decimal places. Okay, that's important. So, and our volume is this. Okay, so we work out the number of moles of the sodium carbonate. Okay, to 4 decimal places. I'm just going to leave it like this. 2,4 times 10 to the 0.3 mole. Okay. Otherwise, you could also write that. You could obviously just write that as 0,0024 mole, if you prefer. I prefer the scientific notation. Okay, it's easier for me. Okay, so now we have this thing going for us. Okay, so now what we need to do is we need to work out use our mole ratio to work out what moles would be able to neutralize. Okay, we need the number of moles that will neutralize this amount. So we need to find out the number of moles of HBr solution that will neutralize this amount of sodium carbonate. Okay, so we use our mole ratio and we're using NO2 carbonate. So this gap should be a bit smaller, but we're using NO2 to HBr. Okay, so from our balance equation, we know that it's 1 to 2. So 1 is to 2. And we know our moles of sodium carbonate is 0.024. I said I'd write scientific notation, but I'm writing it like that now. But anyways, and we just times this by 2. So this is 0.0048 moles. Okay. So what we have now is we have the number of moles. Okay, so we've got our goal. Now we can work out the concentration. Okay, so again, let's say now we're working with HBr. Okay, and what we have is we're using this equation of the concentration is equal to N over V. So we know our number of moles, and we have our volume, 0.0152 decimeters cubed. And if it wasn't decimeters, we would have to convert it, but luckily it is. So 0.048 divided by 0.152, and work to 4 decimal places. Well, they say work to 4, but we would report our answer as 2. So it should be 0.32. Never mind. It has to be 4 decimal places. Okay, because they want 4 decimal places. I don't know what I was doing there. Okay. 5, 8. Okay. And the units, don't forget the units, moles per decimeter cubed. Okay. So yeah, the reason I wanted to put it to 2 decimal places is because I said each step of the calculation. So I mean, here it's the solution part. I mean, it's at each step of the calculation. Yeah, I don't know. I might have lost some marks there, but yeah, I would have put it to 2 because I mean, I understand here 4 decimal places, but now I'm no longer calculating. I'm putting a final answer. Okay, maybe that's just me being a bit overthinking it a bit, which I know other people struggle with too. But I thought I'd just share that. So it happens to me too. But anyway, that is the final answer over there. Okay. So let's move on. Question 6, voltaic cell. So we're in electrochemistry now. So I know a lot of people struggle with this, so let's tackle it. So we're given a standard voltaic cell, and it's set up and shown below. Okay. So we're getting some half cell A over there. It's got some tin ions over there. It's got some platinum electrode. And on the right, we've got some chromium ions. In the middle, we got the salt bridge, potassium nitrate. And we've got that voltmeter connecting them, completing the circuit. Okay, let's jump into the questions. And first question, what is the benefit of using platinum gauze rather than a straight piece of platinum wire? Okay, so why did they use this gauze instead of just one piece? Okay, so what happens is if you're using the gauze, obviously you have a bigger surface area. Okay, so we get a bigger surface area. Okay, and then if you have a bigger surface area, there's 3 things you can say now. So I should have wrote area, so a bigger surface area. So you can either say that it's a better catalyst, all right, because you have a bigger surface area. So you would get 1 mark for bigger surface area, and then you have one of these 3 options. Okay, for your second mark, you have to say it's a better catalyst. Okay, so the reason it's a better catalyst is because obviously the reaction takes place on its surface. So if there's more surface area, there's more places for it. Essentially, it could be a better catalyst because there's more places for the reactions to take place, the electron transfer rather. And then you can say that it increases the rate of reaction. That's another thing. Okay, because also remember our factors that increase rate is one of them state of division / surface area. So it increases rate of reaction. Okay, so this increases the rate of reaction more than a wire. Okay, and it will increase the current of the cell. All right, so this one, increase current of cell. Okay, so very important with this one. So some of you might be saying, whoa, hold up. Because we know that the EMF is always constant, right? The EMF of these cells is always constant, right? So how can you say increase the current of the cell? Okay, so the EMF is always constant. It's always constant. So the EMF is determined by what electrodes you use from the standard electrode potential table. Okay, but things that can increase current is things like surface area. If you have a bigger surface area, there's more place where electron transfer can take place. So there's more electrons, which means there's more current. Okay, the rate of flow of current. Remember, current is the rate of flow of charge. So if you have more charge, you have more current. Okay, so don't let that confuse you. I know people relate EMF a lot and current. I know it is a bit confusing, but they're separate. Let's just think that they're separate in galvanic electric chem. Okay, so I hope everyone's with me there, and we cleared up maybe some misconceptions. All right, now we need the symbol of the oxidizing agent. So the oxidizing agent is the thing that is reduced, and the thing that is reduced is the thing that gains electrons. So the thing that gains electrons becomes more negative. Okay. So what we actually need to do is we're going to have to go to our table, our standard electron potential table, electrode potential table rather. Okay, so we got to keep an eye out for these tin things and this chromium. Okay, so remember a positive value in that column on the right where they say E/volt. The positive value means they're happy. Okay, so it's happy to go in that direction. Okay, so positive value means it's happy to go in that direction. So for example, all the way at the bottom, fluoride, sorry, well, that's just fluorine gas. Fluorine gas is very happy to be reduced. That's why it's that plus 2,87. All right, so that means it's happy. All right, something there at the top, lithium, and lithium ion plus electron, it doesn't want to gain that electron. That's why it's a negative. Okay, because remember, all of these are written as reduction on the left, all written as reduction. Okay, that's why they're plus. You'll see everything's got plus, E, plus 2E. So they're all written as a gain. Okay, so we need to find out one of them is going to be at the bottom. Okay, the one at the bottom. So the one that's positive, one is going to be positive and one is going to be negative. Or they might both be positive, but the one that is more positive will be the one that is reduced. Okay, so let's have a look at that. So if we work from the bottom up, okay, because we're looking for the thing that is reduced. So we're looking either for tin, some SN2 plus 4 plus, or we're looking for chromium 3 plus. All right, so if we work up from the bottom, we keep going up. So I just went past Fe3 plus, still not seeing anything. Getting a bit concerned now. Not concerned, because I see SN4 plus 2E then becomes SN2 plus. Okay, so let me write this. So this would be my reduction half. Okay, and my reduction half is SN4 plus 2E reacts to give us what's a one-way reaction. One way to SN2 plus. Okay, so that is my reduction half. And the reason I know it's my reduction because it's the first at the bottom, right? If I keep going up, right? If I keep going, you'll see chromium is above. Okay, so chromium, it doesn't want to be reduced. Remember, it's a negative. So chromium actually wants to be oxidized, all right? Or oxidation. Wait, how am I spelling? Oxidation. Okay, so the oxidation half reaction is not going left to right, it's going right to left. So chromium wants to lose electrons. Okay, so chromium wants to lose electrons like this. Okay, I hope everyone is with me. Okay, so if the electron's on the left, you have reduction. If it's on the right, you have oxidation. All right, so we have these two things now, and we're looking for the oxidizing agent, So it's the thing that is reduced, the thing that gains electrons. Okay, so do you see how this thing is gaining electrons? So our oxidizing agent is SN4 plus. Okay, Hope everyone's happy with that. All right, and actually, when I was prepping for this, I put this table, but I didn't discuss it. But let's have a look now. Okay, so essentially, everything here in this column, this whole column is written as reduction. Okay, all of these is reduction. Right, because remember reduction, if you look at oil rig, the rig part, let me write the oil part, the reduction is a gain. Okay, so you'll see all of these on the left, the gain electrons, plus E, plus E, plus 2E. Okay, they're all written as a gain. Okay, and if this value is a negative, it doesn't want to gain. It wants to actually go this way, all right? But if we start looking from here below, right, then they start becoming positive. So these things actually want to be written this way. Okay, they want to be written left to right. Okay, so that's why if I look from the bottom up, I'll see that tin here. Okay, so here's my, this would be my reduction half reaction. Okay, because it wants to go this way. See how it's positive? It wants to go this way. All right, but if I keep looking up and I keep going, I'll see chromium is here, but chromium is negative, so it doesn't want to go this way. What it'll do is it'll go that way. So that's why that was my oxidation half reaction. Okay, so I hope this was a bit less hand wavy than my explanation before. Okay, I should have seen this, my fault, but I hope it's clear now if it wasn't before, or it's more clear now. Okay, let's keep rolling. Now, write the cell notation for this cell. The conditions and state symbols are not required. Okay, so there are a bunch of rules for this. You can find the rules on your SAGs, but essentially what you do is you go, the catalysts are on the outside. Okay, so catalysts go on the outside. We use a double arrow to represent the salt bridge. So let me write down. Let's do a bit of diagrams here with Brandon. Okay, so double arrow, vertical arrow, this is our salt bridge. Salt bridge. Okay, single arrow, that represents a phase change. Okay, we use a comma to separate things in the same phase. Same phase. Okay, and what we do is we write the anode first. Okay, that's another rule. Anode first. Okay, and remember anode, if we look at this O, an anode is where oxidation takes place. Oxidation. So anode, oxidation. You see that O, oxidation. Okay, so we're going to do that oxidation half first, then the reduction half. Okay, and also very important, another rule is that we put the catalysts on the far left or far right. It depends which cell it's in. You'll see now. Okay, but catalysts at end. All right, so catalysts are at either end. Okay, let me write that. Either end. Let me put that with a little star. Okay. So let's have a look. So anode is first. Okay, so our oxidation half reaction is first. So where did we write? So here's our oxidation half. Okay, so we can see that chromium is being converted into these ions, chromium ions. Okay, so they say state symbols are not required. Okay, so we say Cr. Normally we'd have to say S over here, but it's not required in this case. So we have chromium, and now we know chromium is being converted to these. So these are aqueous. This is solid, this is aqueous, and those electrons, no, this is aqueous. All right, so there is a phase change. It goes from solid to aqueous. So we write Cr, phase change, and then we write Cr3+, and again here, if I wanted state symbols, we put a little aqueous here in a bracket. And now what happens, we have our salt bridge. Okay, so let me change colors here. So now we got our salt bridge. Now what we do is we write our reduction. So we did anode and now cathode. So we did the oxidation, now we do the reduction. Over here is our reduction. So we have SN4+ is changing into this, SN2+. But they're both aqueous, so there's no phase change. Okay, so we put this SN4+ first, okay, because that's the thing that's being changed, right? Then we put a comma, because there's no phase, same phase, right? Let me make this a bit clearer. 4+, okay? Then we have, it's being converted into SN2+, okay? But now, important, where there's a phase change because our catalyst is solid. Okay, we don't actually need that state symbol. Okay, but this is what I mean by the catalyst at the end. Okay, so you see our catalyst is all the way at the end over here, right? If there was a catalyst on the left, what you do is you would put it over here. Okay, you guys with me? So yeah, if there was a catalyst that was also solid over here, it would be a comma. Okay, because there would be no phase change. Okay, but my main point is that catalysts go at the end. So don't try to put a catalyst in the middle. It's on either end, either extreme. Okay, so that is the cell notation for this cell. All right, so the punctuation is important. So the commas are important, the lines are important, all of that stuff is important. Okay, let's move on. So now they say consider the electrolyte solutions in the cell. Okay, so in half cell A, we have that tin chloride, both of those tin chloride solutions. And half cell B, we have that chromium sulfate solution, and then we have the potassium nitrate in the salt bridge. So we have to name this compound, this tin Cl4. Okay, so what we can say is, so it's a metal and non-metal. Okay, so we know that the valency, if we do SN chloride, we know that the valency of chlorine / chloride is 1. And we don't know the valency of this thing, but we know when we cross them, we get not SN4, we get SnCl4. So do you see how then this valency has to be 4? Okay. You with me over there? Okay, so what we can do is we can say that this is Sn, and we use stock notation here, Sn, so this should be tin. Okay, so you say tin 4 chloride. Okay, but what they do accept, they do also allow you to say or, so don't put the slash in your test exams. You can also say tin tetrachloride. Tetrachloride. Okay, because 4 is tetra. All right, and then also if you somehow knew the actual chemical name for this, you could call it stannic chloride. Stannic chloride. Okay. So, but yeah, you're definitely not expected to know that. If the first time you're hearing that, that's all good. When I saw it, my first time hearing it as well. So don't worry about that. Okay, it's just tin 4 chloride. Then we have to identify the anion. So anion is a negative ion. Okay, other than nitrate, that will be in higher concentration in the salt bridge after the cell has been operating for some time. Okay, so if we look at our half cell A, so in half cell A, what's happening in half cell A again? If we go up a bit, in half cell A, this is half cell A, and this is half cell B. So in half cell A, what's happening is we're getting more negative, right? Because we're gaining electrons. Okay, we're going from 4 plus to 2 plus. So we're getting more negative, right? So this thing is becoming more negative. Okay, it's becoming more negative. Then on the chromium side, in half cell B, it's becoming more positive, right? Because we're producing these Cr3 pluses. Okay, so this is becoming more positive. Okay, so now we need to think, okay, what anion is going to be in the salt bridge? Okay, so what this anion movement is, so obviously in this solution we also have chloride ions, okay, because it's this tin chloride. So there's chloride ions here, and then here was chromium sulfate. Okay, so 4 3 minus. Okay. So those are the anions we have. Okay. But if we have a look here, this thing's getting more negative. So what's going to happen is this thing's also negative. So this thing's going to want to move, right? So it's going to want to move because like charges repel, but it's also going to want to move to neutralize this positive charge. Okay. So with the anion that is going to be in a higher concentration in the salt bridge is this Cl minus ion. Okay. Okay. But I missed a question. So that's the ion. And we have to explain the direction of the motion, so of the movement of this anion in this question over here. And to explain it, there's a few different things. So there's two reasons. You can say it's moving to balance the positive charge in the oxidation, so in half cell B. So we could say to balance positive charge, right? So its movement is to balance positive charge when chromium is oxidized to Cr3 plus. Okay, because we're getting a whole bunch of these positive things, so we need to balance that positive charge. Okay, so that's option one. Or what you could say is, well, we're getting all these negative charges over here, so it moves because of all these negative charges. Okay, or you could say because the movement is because due to an increase, because there's due to an increase in negative charge. Okay, in that half cell A, there's an increase in the negative charge because of the reduction of the tin 4 plus to tin 2 plus. Okay, so two options there. All right, then 6.5, we have to give two changes that could be made to the salt bridge to decrease the internal resistance of the cell. Okay, so just to the salt bridge. Okay, so there's a few here. There's actually 4. Okay, so if we look at our salt bridge, let's look where it was maybe a bit bigger. Yeah, in this bigger diagram. Okay, so if we look just at our salt bridge over here, we need to say, okay, how can I decrease? They're asking to decrease the internal resistance. Okay, so how can I decrease the internal resistance of the salt bridge? Okay, so it's very similar to resistors, some of the conditions that affect resistance of normal conductors, for example. If we shorten the salt bridge, what will happen is will decrease the internal resistance. So a shorter salt bridge, also a wider salt bridge would be better, and also a more concentrated potassium nitrate salt, or we could even use something that's more conductive. Okay, so there's 4 options there. So I'll write them for us. So you could say you use a shorter salt bridge. You could use a wider salt bridge. And you could use or you could use a more concentrated. So this is short for concentrated potassium nitrate salt, or solution rather. It should be solution. And then also you could say that you could use a more conductive salt. So more conductive salt in the salt bridge. Okay, so if you look at this, it's actually very similar to resistors, right? Or resistance of a conducting wire. Okay, so if I draw a conducting wire over here, you guys know my drawing, but anyways, if we draw this conductor, so if this thing is narrow, so if it's not wide, the resistance is going to be higher, okay, because the charges are going to be like constricted, right? You can think if you use like a really skinny straw, okay, it's tough to bring up the liquid, right? So if it's wider, it's easier, well, to a certain extent. Maybe not the best analogy, but it's more like constricted. You can think of a doorway. If you think of your class hall or your school hall, like hallway, I mean. So if you have a very narrow hallway, then there's going to be a lot of resistance. You're going to be bumping into people, right? But if it's wider, there's more space, less resistance, okay? And also if it's shorter, you have to go through like less students to get to your class. So there's less resistance there, okay? And then if you use a more conductive salt, more concentrated salt as the solution rather, more conductive solution of that potassium nitrate salt, then it's easier for the charges to move, right? So it's easier for the charges to move along in the salt bridge. And then also if you have a more conductive salt, obviously if it's more conductive, there'll be less resistance. Alrighty. 6.6, they say a soluble chromium sulfate salt is used to prepare the electrolyte for half cell B. Assume that the salt dissolves completely. Calculate the mass of chromium sulfate that should be weighed out in order to prepare 0.25 decimeter cubed of the 1 mole per decimeter cubed chromium ion solution, electrolyte solution. Okay, so we're gonna need a mass. Okay, we need a mass of this thing. Okay, and we need to prepare this amount of 1 mole of the chromium ion electrolyte solution. Okay, so what we're given here, we're trying to find a mass. Okay, so I'm going to write up, we're trying to find a mass of this thing. Okay, the mass of that thing. So we're given a concentration and a volume. Okay, so we can work out the number of moles of Cr3 plus. Okay, so very important. This is especially when my labeling thing that I recommend comes in handy. So we have that N is equal to Cv. Okay, the number of moles of chromium ion is equal to the concentration is 1 and the volume is 0.25. It's in decimeters cubed, so we're sorted there. So that's 0.25 mole. Okay, but it's mole of this chromium ions. Okay, now we need to work out the moles of this chromium sulfate salt. Sulfate salt, rather. So what we have to do is we have to do a mole ratio. Okay, so let me start off with the ion rather. Cr2SO4 3. Okay, so 1 mole. So let's have a look. So if we want to create one of these things, right? How many chromium ions do we need in here? You'll see we need 2. So 2 of these will make us one of these. Okay, because we need these 2 chromiums to then make one of these bigger units. Okay, so this is our mole ratio. Okay, so we have 0.25 moles of this chromium ion. So we just divide that by 2, or you could use some of the other methods we have discussed in this video. So that's the moles of this chromium sulfite salt. Okay, so now we label this properly. SO4 3. So we're going to say number of moles is mass over molar mass. And we know the number of moles, which is 0.125. Okay, and we're trying to find the mass. The molar mass we can find on our periodic table by adding everything together. So if we do 2 times chromium, so where's chromium? So we say 2 times 52 plus 3 times sulfur, which is 32, plus 12 times oxygen, which is 16. So that we get 392 for the molar mass. Okay, so therefore the mass of the salt that we need to weigh out will be, we times those numbers together, 49 grams. Okay, so we'll need 49 grams of that salt to then form that concentration of chromium ions. Okay, then they give us this photo here of the bonding in solid chromium. It's represented by this in the diagram below. Name this type of bonding. Well, solid chromium is a metal, so this has to be metallic bonding. Okay, and you'll also see that obviously the electrons are delocalized. So then that's how we can also tell that it's metallic bonding. But obviously chromium is a metal, solid chromium, metallic bonding. Okay. Then we have to reference the diagram. We have to explain why chromium can be used in an electrode in half cell B. Okay, well, we use an electrode rather, because it has these electrons that are free to move. Okay, these electrons are free to then move through the external circuit to the tin side, there by that platinum gauze. Okay, so that's literally what we have to say. So the electrode, it's really important that our electrodes can conduct electricity. So we will say, well, it can conduct electricity. Can conduct electricity. And we need to reference the diagram here. So it can conduct electricity because the delocalized electrons are free to move. Okay, so remember, current is the flow of charge. Well, if the charges are free to move, then you're going to be having flow of charge and current. So you're going to have a conductor. So it can be used because it can conduct electricity because the delocalized electrons are free to move. Okay, I should say electrons, delocalized electrons are free to move. Okay, and then that concludes question 6. In question 7, we're given this. We're saying that water can be electrolyzed using a Hoffman voltmeter illustrated below. So I know this thing can look a bit intimidating, but let's just take it easy. So if we start up here at the top, we see we got water plus this sodium sulfate salt and bromomethyl blue indicator. So they say that the sodium sulfate is used to increase the conductivity of the water, but it doesn't participate in the redox reaction. Okay. And then you can see here we got this anode, and then on the anode side, oxygen is being produced, and on the cathode side, hydrogen gas is being produced. Okay, so over here, this is a gas. Okay, we're using this to collect the gas. So what's going to happen is something is going to be oxidized over here, and what's going to happen is it will bubble. These things will bubble, form a gas, and then they will collect up here. Okay, so that's why it's made in this way. So I know it looks a bit weird, but let's just take it easy. So we know it's an electrolytic cell because we have a battery. Okay, so we're supplying energy into the circuit or into this process here. So yeah, so we know we're converting electrical energy into chemical. Okay, so let us have a look. So they say here the equations for the half reactions. So they give us this over here. So you can see that on the one side, water is being reduced. Okay, we know it's reduced because remember oil rig, RIG, reduction is gain. So you see how we got a plus electron over here. So this is the reduction half. Okay, I'm going to write red for reduction. And then obviously this side has to be the oxidation part. And obviously because the electrons are on the right, it's the oxidation part. Okay, so again, so if I write anode over here, anode, so there's a few differences between electrolytic cell and galvanic cell. So firstly, you'll remember in the previous question that O stands for oxidation. All right, this is consistent between both the galvanic and the electrolytic. So the anode is always where oxidation takes place. All right. In a galvanic, all right, for galvanic, I'll put it up here. For galvanic, when we say anode, you can, if you want to remember, is the anode positive or negative, you can remember that anode is a negative what do you call these things? So obviously the anodes and cathodes, but electrodes, there we go. So anode is a negative electrode. Okay, so in galvanic, the anode is, we know this oxidation takes place there, but we know it's a negative, okay, so that N, negative electrode. So in galvanic, the anode is negative. Okay, but in electrolytic, it's still oxidation, but the anode is now positive. Okay, so I'm going to put this here. I know the anode will be positive and the cathode will be negative. So I might need this. Okay, I just thought I would include this. All right, just to remind us, we might need it. Okay, so then we see also that here they say that the anode and cathode are both made of platinum. Okay, so I don't think I've missed anything there. We got a rheostat, an ammeter, and a battery. Okay, so let's not worry too much about the rheostat and stuff like that. But let's just have a look here. So water is being oxidized and we're producing oxygen gas. So these little bubbles here are oxygen, and that's why we have this oxygen here. And then this side, water is being reduced, so it's gaining electrons, and that's why this hydrogen gas is being produced here. Okay, so we're obviously going to bubble up some hydrogen gas here. And now let's get into the questions. So they say, what is the benefit of using platinum rather than another metal? Okay, so this is again just a memorization from theory. Platinum's inert, okay? So inert just means it doesn't react, okay? It won't react with anything. So obviously we're trying to produce this oxygen gas and hydrogen gas, and we don't want any type of electrode interfering with that process. Okay, maybe contaminating it and making some byproducts that we don't need or want rather. All right, and then 7.1.2, so state whether the anode is connected to the positive or negative terminal of the battery. Okay, so we're in electrolytic. So it is no longer a negative electrode, it is now positive. Okay, because we're in electrolytic. So that's what I was just talking about on the previous slide. Okay, so it's positive. Okay, it's positive. And then let's just say how electrons will flow in this case. Okay, so in the anode, we have this oxidation. Okay, so what's happening is we're gaining electrons here, and at the cathode, we're losing. Sorry, no. At the anode, we're losing electrons, and at the cathode, we're gaining. Okay, so in this case, the current will be from the anode to the cathode. So it'll be from the anode to the cathode. So it flows from the positive to the negative. Okay. It is different in the galvanic. That's also another thing that's different with the galvanic. Okay. So in the electrolytic, because we have this battery that all looks like this. So remember that long leg is the positive. So what will happen is we flow from the positive to the negative. Okay. So I know that's not in the question. I just thought I'd mention it. Let's look what happens with the electrolytic over here. Okay, so let's get rid of some of this and let's identify what's cracking here. So this is the reduction half over here. So I'll write red, and here is the oxidation half. Okay, so we know in galvanic, oxidation happens at the anode, and in galvanic, a negative electrode. So we know this is negative, so then this must be positive. Okay, but now let's think of the flow of electrons. So over here, chromium forms these chromium ions, if you look here at the reduction, and what happens is it frees electrons. So there's a whole bunch of electrons that come out over here, all right? There's some free electrons. So these electrons have to flow to this side, right? Because on this side, we have reduction. So what's happening is these tin ions are trying to gain electrons. Okay, so over here, it goes from negative to positive. Okay, here's the negative side, and here's a positive side. So that's also opposite in galvanic. Galvanic goes from negative to positive, and if we go down to electrolytic, electrolytic goes from positive to negative. Okay, like normal. So electrolytic is like a normal current flow that we deal with in electric circuits and in physics. So positive to negative. Okay. So I just thought I'd discuss those two things here. Okay, we've had a lot of sidetracks in this paper. Hope it hasn't been too distracting. And yeah, I know I've said it a million times, but I hope it's been helpful. Okay. Sorry if I repeat some things. Sometimes I have to do these videos over multiple days. So sometimes, you know, we're getting old here, my memory. Not what it used to be back in the day. But yeah, okay, let's continue.
So editor Brandon here again. I thought I'd just add something here. So in galvanic cell, well, in electrochemistry in general, so we often work in alphabetical order. So what I mean by that is a lot of the time we go anode to cathode. Okay, so a mnemonic you can use to remember is what we call fat cat. Okay, so it stands for from anode to cathode, fat cat. Okay, from anode to cathode. So no matter if you're in the galvanic or electrolytic, your electrons will always flow from your anode to your cathode, okay, alphabetically. And also, importantly, when we do the cell notation, we always do anode first, okay, A before C. So anode, then cathode.
So point 3, so we have to classify this reaction as oxidation or reduction, give a reason. Okay, well, it's very clear. The electrons are on the left. Okay, reduction, Remember oil rig? I know I'm repeating this. Okay, my memory's not that bad. Okay, oil rig reduction is gain. Okay, so obviously it's a reduction, right? Because we're gaining electrons. Okay, the electrons are on the left. That's also how you can identify. So you could literally say that reduction because electrons are gained. Okay, I would do that one. That's the easiest one. The memo does allow alternative options where you talk about the the oxidation number of H. You could discuss that. And you could also discuss that this reaction takes place at the cathode. So it has to be reduction at the cathode. All right, so you can look at the memo for those explanations. I prefer this one. This one's super easy, so I'm not going to write the others. Okay, let us have a look. So calculate the cell potential E cell with that theta at the top for the decomposition of water under standard conditions. Okay, so we have two equations that we can use here from your formula sheet. I much prefer the top one. The bottom one, for me, you have to do some weird thinking stuff. Okay, so I learned. I've now got the standard electron potential table. Okay, but let's have a look. So we know the cathode is where reduction takes place, and we know the anode is where oxidation takes place. Oxidation. Okay, and then over here, I've even repeated these the reactants for us. So we know the top is reduction and the bottom is oxidation. Okay, so we need to look for this thing. Okay, and then we're going to have to write the cell potential for that. Okay, but I want you guys to just keep your eyes out for something. We're going to have to be a bit careful here. Okay, we're going to have to be a bit careful. But anyways, so let's go look for this on our standard electrode potential. Okay, so I'll start at the top or bottom. It doesn't really matter. Anyways, we look for this and we find it. Make sure that it is exactly what we see. Okay, so we got two waters, two electrons, hydrogen gas, plus two O2. Because remember in the previous section, I made a mistake where I didn't get the right one, right? I think it was the nitrate, between these two nitrates. Okay, you see how these two look super, super similar, but you got to make sure the one makes NO2 and the one makes NO, nitrogen monoxide versus dioxide. So you got to be super careful. Okay, so if I look here with this red arrow, I go back and I make sure that yes, they're identical. So this is definitely the thing I have. Okay, so what I write is I say E cell with this theta thing at the top is equal to, well, I'd have to write the formula. Obviously, you get a mark for the formula, E cathode minus E electrode. Okay, and if I do that, I know my electrode potential over here is, for the cathode, is negative 0.83. So I literally just write what I see there. Okay, then negative, and I wrote your electrode. I don't know why I wrote electrode. It should be anode. Yeah, it should be anode over here. All right. So if we look now for the anode, we are looking for this reaction over here, where water is oxidized. Okay. So, but also very important, just remember, all of these are written as reductions. We spoke about it, the gains. So technically what we're looking for is, we're going to look on this side. Okay. Yeah, or what you could do is you could ignore these and then look at these ones. Okay, I'm actually going to do that. I'm going to ignore these and I'm going to look where we have water, right? So I'm going to make sure that I'm looking for two H2Os, then form O2 plus 4H, that thing over there. So you'll see what I mean in a second. Just stick with me here. So I'm looking for 2H2O. Okay, looking for 2H2O. So we keep going. This is close, but not quite. Keep going here. We got 2H2O. Okay, I gotta, yeah. Okay, so we have this. 1 second. Okay, sorry, I had to sneeze. So if you have a look here, this is the one we have. Okay, so just be careful. You see how it's written as an oxidation. Okay, so you see how it's written this way, right? But you'll see that we see it the opposite way. Okay, remember they're all written as oxidations, but it's fine. We can read from right to left in this case. Okay, So very important, what we do is we don't change this value. Even though, right, this thing is written as O2 plus 4 H plus, right? Even though it's written not in the same way as this, right? It's not written in the same way. We don't then change this positive to a negative. We just write this. We just write this positive 1 plus 1 comma 2 3. Okay, you guys with me there? All right, and if we put that in the calculator, we get negative 2,06. Very important. We need the units, volts. Okay, good. So that's our answer there. And then the answer here is the reaction spontaneous or non-spontaneous. Give a reason in terms of the calculated cell potential. Okay, so obviously we know electrolytic cells are non-spontaneous. Okay, we have to supply electrical energy. So we say non-spontaneous. Non-spontaneous. Okay, and the reason we can't just say, oh well, it's electrolytic, because they say in terms of the calculated cell potential. Okay, and then because this thing is negative, then it is non-spontaneous. Okay, so you can say that because the E cell is less than 0. Okay, or you could just say negative. It's the same thing. All right, let us have a look at the next question. So they say bromomethyl blue is a weak acid indicator that is yellow in acidic. So it's yellow in an acidic solution and blue in alkaline. And it can be represented as HIN, and the equilibrium that occurs in solution can be represented as below. Okay. So here's our indicator. They're just representing it as this thing over here. Okay, because indicators have like weird complex formulas. But anyways, here's H of indicator. All right, so I know it looks a bit funky over there, but it's not panic. So it says, what is the color of this ion? Okay, so the anion of, well, I said the deprotonated form of the indicator. Okay, so let us have a look. So bromomethyl blue, this is bromomethyl blue. So I'm going to write this as BB. This is bromomethyl blue. This is our indicator, okay? So it is a weak acid. So do you see on this side, it should be yellow because it's acidic. But on this side, this is the acid, right? So this is the acid. And then obviously this is the deprotonated form. So this is the conjugate base. So this thing is a base, okay? So what's happening is, I know we have these hydroniums, okay? But the thing is, this thing is being deprotonated. So the color of this thing, because it was an acid, now its conjugate base is blue. Okay, it's blue. So I know we are producing these hydronium ions, but this thing is blue. Okay, this thing is blue. All right. Then they say, what color of solution will be, so what will be the color of the solution around the cathode? Okay, so let's go up to the cathode. Okay, so here's the cathode. And at the cathode, we have reduction going on. So I'll write this first. So we have this. We have 2H2O plus 2E, and then reacts to form. I'm just running out of space. So 2OH minus plus H2. All right. So that's what we have going on at the cathode, this reduction. So you'll see what's happening here is, what are we producing? Producing this hydroxide. So the concentration of hydroxide ions will increase. So if that happens, we know we are becoming more basic. So our pH will get higher. But they ask for the color. So the thing is becoming basic, and the thing is blue and alkaline, or basic. So it will be, we should see blue. Okay. Everyone happy with that? Now, hope everyone was. Obviously, I can't get any live feedback from you guys, but hopefully you guys are all good. Let me know if you're not in the comments again, if you need anything. Okay, so it says a constant current of this 0.05 amps is maintained for 1.5 hours by carefully controlling the rheostat. Calculate the amount of charge that passes through the solution in this time period. Okay, so we have current and we have time. So very important, time is in hours. We're going to have to convert that to seconds. Okay. I think let's just put a little star. Remember, that needs to be in seconds. Okay. And let's say calculate the amount of charge. So the symbol for charge is Q. All right. You'll remember from physics, if we do there's electrostatic forces, we use Q for charge. Okay. So you see in our formula in the bottom left, we have this formula Q is equal to IT. And what we can do is just plug in all of our values in. Okay, so our current is 0.05. Our time we need to convert to hours. Or, sorry, minutes, not even minutes. What am I saying? Seconds. Okay, so we convert to minutes and seconds. Okay, so the way we do that is we say 1,5 times 60. That'll give us the amount of minutes. Then you'll see that's 90 minutes times 60 again for the amount of seconds in 1 minute. So you'll see that this becomes 5,400. Okay, and if we put that thing in our calculator, we get 270. Okay, so 270. I don't know why my twos are changing. How do I normally do it? There we go. I normally do it like that. 270. Okay, and then the units over there should be coulombs because charge is measured in coulombs. All right. Now they say hence. Okay, that's important. Calculate the volume of oxygen gas that will be produced at STP in this period. So they're asking for the volume of oxygen gas. All right, but they say hence. So there's a lot of weird things going on over here. But if we know the number of moles of electrons, which we can work out using this value over here, then we'll be able to work out the number of moles of oxygen, right? Because our formula we're going to be using is N is equal to V over Vn. Okay, we know we can use the molar volume because we're at STP. Okay, so we need to find volume. We know the molar volume, and if we have this N, which is our goal, then we're sorted. Then we can find the volume. But to find the number of moles of oxygen, we're going to first have to find out the number of moles of electrons. Okay, and we know we're going to have to find the number of moles of electrons because of, they say hence, and we just calculated this C over here. Okay, so this formula is not given on your formula sheet. So again, this is a bit of memorization. You have to know that the number of moles of electrons, okay, we're working with electrons here, is N is equal to Q over F. Okay, this is the formula. Okay, so Q is the charge, which is 270, all right, divided by Faraday's constant. So F is a constant. So you see on our formula sheet, it's 96,500 coulombs per mole. Okay, so if we do that, we get this value over here. So I'm going to leave it. Remember, we shouldn't round. Okay, too much here. So I'm actually going to leave this thing on my calculator. But yeah, it becomes this. But I'm going to leave this in my calculator so we don't round. Okay, mole. All right, so I know how many moles of electrons I have. So what I'm going to do is I'm going to do a mole ratio from electrons to oxygen. Okay, and if I do that, I know that my normal ratio is 4 to 1. But what I currently have is 2,80 times 10 to the minus 3. And sorry, I keep changing these twos. I was giving a lesson in Dipslit this weekend, and someone was struggling to identify my twos. I call them Zs, so now I'm self-conscious. So sorry about these twos changing. Sometimes they're looking like this. Okay, but that's a 2. And then our oxygen we need to find out, but what we do is we just take this thing, divide by 4. Okay, so again, I keep the thing in my calculator. Okay, and I divide by 4. And what I get is 6,99 times 10 to the minus 4. Okay, so what I do now is I'm going to use this formula over here. And I'm just going to go up here. I'm going to say, okay, well, we're working with O2 now. So this is our formula we're going to use. And we're trying to find volume. We know the number of moles is 6,99 times 10 to the minus 4. Okay, you could also write this in decimal format, non-scientific notation. I mean, I just don't prefer that. I don't like all the zeros. Okay, but essentially this thing basically becomes more or less this. Okay, once you round it to 4 decimal places. But anyway, that's our number of moles. That's the volume we're trying to find, and we know our molar volume is that. Okay, so if we take, again, I wouldn't round on the calculator. I would take the value that here that wasn't rounded, that we divided by 4, I'd keep it on the calculator, and then I'd say that times 22,4, and what I get the volume is, I'm going to report the volume to 2 decimal places, so I get my volume as 0,02 decimeter cubed. Okay, that would be my answer over there. Okay, to 2 decimal places. So that's how we work out the volume of oxygen gas. Okay, yeah, that's what you can do there. All right, I just want to show you one other thing. So I prefer this method that I showed here. Okay, I prefer it. I know you have to memorize this formula, which isn't ideal, but I think it's easier, and I do think schools do teach that formula. It is on the stacks. You do need to know that formula. Okay, but sorry about the scraping noise. It's me erasing. But anyways, let's have a look. Another way I would do is, we know this charge, okay? But we also know that we know the charge of 1 electron, okay? So it's given on your formula sheet as E, okay? That was a Freudian slip. It's given on your formula sheet as E, as this, 1,6 times 10 to the 19 coulomb. Okay, so that's the charge of 1 electron. Okay, of 1 electron. But we have this, okay? So if we take this number, 1,6 times 10 to the minus 19, right? Times by the number of electrons, we should get 270 coulomb. Okay, so if we divide 270 by 1,6 times 10 to the 19, what you'll get is that the number of electrons is equal to 1,6875 times 10 to the 21. That's how many electrons we have. All right, but now what we can do is we can use the equation that n is equal to the number of particles over Avogadro's number. What I do is I just take this thing, 1,6875 times 10 to the 21, sorry, times 10 to the 21, divided by Avogadro's number, which is 6,02. Where is it? There we go, times 10 to the 23. And if I do that, I get, divided by 6.02 times 1023, I'll get 2,8 times 10 to the minus 3 mole. Okay, which should be pretty close to what we had before. Okay, what we had before was this. I'm going to be showing it in a second. What we had before was 2,7. No, we had the exact same thing last time. Okay, obviously without rounding. But we had the exact same thing last time. If you go a bit back in the video, you'll see that we got these 2 different methods gave us the same answer of mole of electrons. So you can choose which one you prefer there. This one that I showed now is more from first principles. But yeah, or you could memorize that equation. But if you don't remember, if you forgot the equation, you can kind of think your way through it. Okay, but otherwise I recommend memorizing the equation. Okay, let's move on. So the chloralkali industry involves the electrolysis of concentrated aqueous solution of sodium chloride. The 3 types of cells used are diaphragm, membrane, and mercury. So what is a concentrated aqueous solution of sodium chloride commonly known as? Okay, think about what like when you buy canned goods of like asparagus or beans or stuff like that, what do they store it in? They store it in sodium chloride solution, what we call as brine. Okay, so it's called brine. Okay, so I guess if you're from Fourways, it's like, I'm sure you know a brine, you know. So it's brine though, not brine. Okay, Bronson. But anyways, let's keep going. So this is just memorization stuff. Make sure you know the different types of cells. Okay, and here again, just recall memorization stuff. Which one of these 3 cells produces the purest and most concentrated sodium hydroxide product, that NaOH? State the main reason. Okay, And again, we should know from theory that it's the mercury. It's the mercury cell. And the reason is because the NaOH is produced in a separate cell. So it's produced in a separate vessel, sorry. It's produced in separate vessel. Okay, because you remember when we work with the mercury, you got the amalgam thing here that then flows down into a separate cell. Okay, so over here, so there's no contamination of, because here obviously we have NaCl, and then what happens is here the Na goes with the mercury, forms an amalgam, flows down. So you see how we don't really have any chlorine down here to contaminate this product, the sodium hydroxide product. Okay, so again, that's just from theory. Okay, and then which one of them produces the least pure NaOH product? What is the major contaminant? And state the reason for this. Okay, so the first one we learn about is the diaphragm, sorry. We learn it from a diagram, but it's a diaphragm cell. Okay, so diaphragm cell. That's the cell that produces the least pure. And the major contaminant, as I said before, is NaCl. And the reason is, well, we allow, in the diaphragm, it's not a selective membrane, okay? So the diaphragm actually allows this chloride to flow through. Okay, it's allowed to go through to the other side. Okay, so the reason here is because the diaphragm cells allows these chloride ions. So it allows the chloride ions to it just allows them through. Okay, allows it through. So it's non-selected. Okay. In question 8, we're starting with organic chem, and we start with organic chem reactions. So this is, I don't really like this section. I hate memorizing. I hate memorizing all the different reaction conditions. But luckily, I don't have to because I'm not writing these exams. When I tutor students, at least I can use a helpful remembering chart or piece of paper. Okay, so anyways, we're given this thing over here. So we start with this compound A. So compound A is, we know it's a haloalkane. Okay, it's got this bromine, which is a halogen. So it's a haloalkane. Okay, and we know it's an alkane because if we draw this thing, you'll see that there's no double bond. So it's an alkane. All right, then reaction I over here, reaction 1 is with hot concentrated potassium hydroxide in ethanol solvent. And then reaction 2 here is we're heating under reflux with dilute KOH, potassium hydroxide aqueous. Okay, so with haloalkanes, there are only 2 types of reactions, okay, that can happen with haloalkane. So either what we can do is you can eliminate the halogen and a hydrogen, and then you can form an alkene, or you can substitute with you can get rid of that halogen and with a OH, a hydroxyl group. And what happens there is you form an alcohol. Okay, so there's only 2 reactions for this bromine, this haloalkane. So when we have this ethanol solvent, okay, when you have this hot concentrated potassium hydroxide in ethanol solvent, this is an elimination. So elim, or not like that. Elimination. So it's elimination reaction, and then we're going to form we form an alkene over here. Okay, and then this one down here, as I said before, this one has to then be a substitution reaction. I'm going to write here sub, and what we form is an alcohol. So this would be an alcohol over here. Okay, and then to form an alcohol to an alkene, what we need to do there is we have to eliminate water, H2O. So what happens there is then this is an elimination. Okay, so reaction 3 will be elimination. And also you can memorize the reaction conditions that if we have this concentrated phosphoric acid over here, then it's elimination. So we're getting rid of our H2O. Okay, so we can see what's going on over there. Obviously, we don't know what compound B and C is yet. We can find it out. But let's have a look. So we need to write the IUPAC name for compound A. Okay, so this is carbon 1, 2, and 3. Okay, the reason this is carbon 1 is because it's got this halogen over there. Okay, so, and we know that there are 3 carbons. Okay, so it is pro. It's prop, right? The suffix, not the suffix, the prefix is prop. Okay, but we also have a bromine, and it's on the first position. So we say 1 bromo propane. Okay, 1 bromo. So we don't write bromide. We change that to bromo, right? That's also why we have chloro and iodo. I don't know if I think it's on the stacks. I haven't seen one with iodine for a while. But anyways, let's have a look at the next one. So identify the homologous series to which compound A belongs to. Okay, so it's a haloalkane. Okay, it's a haloalkane because we know it's got those single bonds if you draw it out, and it's got that bromine. All right, so it's a haloalkane. And then write the condensed structural formula for compound B. Okay, so compound B is when we eliminate an HBr. So we're going to eliminate the HBr. So let me draw. So I'm going to draw what we currently have, right? So I'm going to do the full drawing over here. So I'm not going to do condensed. I'm going to show the full structural. Okay, so here we got got our H's like such. And it doesn't really matter where I put this bromine, but I'll put it here. Okay, I could also put it in the top or bottom position there. But anyway, so this is what we currently have. This is for compound A. But in this elimination reaction, we have to get rid of HBr. So we're going to get rid of that. And then what happens, we get rid of these bonds. So we have to form a double bond over there. Okay, and then this hydrogen is going to have to move over there. So what happens is for compound B, the structural, okay, is going to be C, C, double bond C. Okay, so if you were confused about why the hydrogen moves, let's just have a look at what happens over here. So we know this C has to have 4 bonds around it. So we fill these up with hydrogens. Then this one is already 3, right? You see it's got 3 bonds. So carbon can only have 4. So this one can only have 1 hydrogen. Then this one currently has 2. So we have to give it 2 more. So that's why that hydrogen essentially moves. Okay. So this is the structural formula. They ask for the condensed structural formula. Okay. So what we do is we say, okay, CH3. Okay, the CH3 here. Then what we do is we have CH. Then we have a double bond and we have CH2. All right, that's the condensed structure. Then let's look at compound C. So compound C is when we substitute this bromine with an alcohol. Okay, so instead of that bromine, we don't substitute with the alcohol, we substitute with a hydroxyl group. So instead of that Br, we're getting rid of that Br, substituting this OH in its position. So what happens is the structural will look like this. So again, this still has 3 hydrogens. This one still has 2. This one still has its normal 2. But now this Br that was here is now being replaced with an OH, hydroxyl group. Okay. So then we essentially have this. Okay, so I could write it like that, or I could write it like such. But the condensed structural formula then is just CH3, okay, CH3, then CH2, then CH2 again, CH2, but with the hydroxyl group. So that is the condensed structural formula for compound C. Okay, now I've repeated this thing over here, and they say for reaction 1, state the general type. Okay, so general type are things like elimination, substitution, addition, things like that, right? Specific is when you start talking about things like hydrolysis, dehydration. What are some other ones? We got hydrohalonation, we got dehydrohalonation, uh, things like that, right? Um, what else? What am I missing? We got those specific types. Okay. So they asked for the general type in 1. So the general type for 1, I wrote up here, it's an elimination. So this is elimination. Okay. Then they ask for the specific type for 2. So if we look at the general type for reaction 2, I wrote here, it's substitution. Okay. So that's the general type. But the specific type, we need to think about what is it called when we take a haloalkane and convert it to an alcohol. Okay. So when we take a haloalkane and we turn it into an alcohol, what that is called is hydrolysis. Hydrolysis. Okay. And then again, here's the specific, that was for the specific reaction type. So we know the general type is elimination, but we need to look at the specific name is when an alcohol turns into an alkene, an alkene. And what that is dehydration. Okay, so dehydration. So that should be a capital. Dehydration. Okay. Cool. Now, let's have a look. 8.7. So here, the diagram illustrates heating under reflux in reaction 2. Okay. So let's break this down a bit. So this thing is in a water bath, this type of flask, and you're putting heat into the water bath, the water gets warm, and then obviously that's going to heat up the reactants. But then what happens is you have this condenser thing over here. Okay, so what happens is the things are going to evaporate, right? Some molecules are going to evaporate, okay? And they can't go in this outside, okay? So this thing here I'm putting in green, only water can flow. So we pump water around this middle part. And that water will then cool these molecules. Let me change them to a different color. So these gas molecules, they're going to try to go up. But what happens is they're going to be cooled, okay? Because this water is flowing around. And then what happens, they're going to turn back to a liquid. And then they're just going to fall back in. Okay, so this is what we call heating under reflux. Okay, and they say here, why is it necessary to carry out reactions involving organic compounds under reflux? Okay, and organic compounds are they have very low boiling points, so they become gas super easy. Okay, and the thing is, you want these things to mix, right? Okay, you want these things to mix for the reaction to take place. So if we look at reaction 2 over here, right, you're heating under reflux with this KOH. Okay, so that OH part needs to go and then replace that Br. Okay, but if what happens is you're heating this thing, this haloalkane, if you heat it too much, it's just going to escape. If you don't have this heating under reflux, it's just going to escape and you're not going to react to anything. So you're not going to actually substitute. Okay, so that's why you actually have to heat under reflux. Okay, because the heating under reflux, it normally takes a long time. And obviously, the things have low boiling points. So if these things are just evaporating, they can't react. Okay, so what we need to say is that the organic compounds, so I'll write in full, so the organic compounds, so that they may have low boiling points, okay? They often do have low boiling points, but they may have low boiling points. Okay, and if it has a low boiling point, sorry, not boiling, so low boiling points, and if they have low boiling points, they can escape. So, and can escape from the reaction vessel. Okay. So my explanation there was just to help you understand, but again, this is just a memorization thing. Okay, question 9. Consider the compound pentyl ethanoate. So we should be realizing immediately that that is an ester. Okay, it's an ester. So draw the structural formula of this compound. So pent is 5 and F is 2. So what I'm going to do is I'm going to draw 5 carbons here. That's 4, that's 5. Then I know there's an O that separates the alcohol part from the ethanoic acid part, the carboxylic acid part. So I know here's my pentyl. Then for my ethanoate, I know I'm going to have this carbon, so 2 carbons for S, and then I know I'm going to have a double bond up here because that happens on the carboxylic acid part. Okay, then what I do is I just fill in my hydrogens. Okay, I just fill in my hydrogens. Okay, so here's H, 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 keep going, H, and then this one gets 3. All right, and then this one gets none. Because if you count the bonds, it's got 1, 2, 3, and 4. Okay, I shouldn't have put it like that, but here's 1, 2, 3, 4. So this one has a total of 4. So this one doesn't get any hydrogens. Okay, so this is the structural formula. Okay, and then over here it says circle the functional group of the compound in your formula below. Okay, so the structural formula includes, sorry, not the structural, the functional group includes this, that carbon. Okay, so this is the functional group of a ester. So again, this is a thing you can memorize. Okay. Okay, so let's move on. The reaction to prepare this compound involves 2 molecules combining to form a single molecule. We know it's an alcohol and a carboxylic acid with the elimination of a water molecule. State the general term used to describe these reactions. Okay, so you might be thinking esterification. Okay, but they ask for the general type. Esterification is the specific type. But when you combine 2 molecules to form a single with the elimination of water, that is a condensation reaction. Condensation reaction. Condensation. Okay. So esterification is a specific reaction with an alcohol and carboxylic acid. But the general type is when you combine things and form a water molecule is condensation. Okay. And then they say, give the name of the carboxylic acid that would be used to make pentyl ethanoate. Okay, so that's just super easy. You just get rid of this 8 part and it's just oic acid. So it's ethanoic acid. Okay, ethanoic acid. All right, and then over here they say give the IUPAC name of the compound below. Okay, so let's see what's cracking here. So we got 2 hydroxyl groups here, so we know it's an alcohol. And you might be thinking, oh, this is a methyl group. No, right? Because we have a continuous chain here. You with me? So it's not like a methyl group up here. So if it was a methyl group up here, then it's not part of our longest chain. But here it's part of our longest chain. Okay, so we're gonna label closest to these 2 alcohols over here. So we should label this from like this way. Okay, because if you label it the other way, this is 1, 2, 3, 4, 5. Okay, so you see then the alcohols are on the 5th carbon, and we want it to be the closest, the smallest number then. Okay, so that's why we number from that carbon in the top right. Okay, but now let's think, how many carbons? We got 7. Okay, so it's going to be hept. So we're going to be dealing with the prefix hept. Okay, and we need to think. So it's got single bonds. Okay, so it's single bonds. So we know it's going to be an a heptan. Okay, but when you have 2 alcohols, so normally if it was 1 alcohol, it would be something like heptanol, right? Heptanol. But if you have 2 alcohols, you need to change it. You need to have heptane. So yeah, you're gonna have to have this E. Okay, when you have 2 alcohols, so very important. And if you have 2 alcohols, normally it would be, for example, propan 1-ol, right? But if you have 2, it's going to be diol, all right? And then also very important, but yeah, sorry, I messed this up. this should be propan 1-ol. Okay, but if you have two alcohols, it's going to be changing to diol, and also very important, this has to become an E. You have to add an E if it's a diol. Okay, so let's look. So we have hept. Okay, so it's heptane, okay, we have to add this E because there's two. All right, now we say where these hydroxyl groups are. So both of them are on the third carbon, all right, and there are two alcohols. So it's no longer heptane, like 3-ol, it's now diol. Okay. So if there was only one, then it would be heptan 3-ol, right? But because now there's two, we say diol and also add this E. So not heptan 3-ol, it's now heptane 3,3 diol. Okay, so that is the name over there. I actually shouldn't have crossed out that name. All right, I'll write it again first. So it's heptane 3,3 diol. That is our name over there. Okay, so let's see what is happening here. So we got this reaction over here where we have these carbons, 13 carbons at 28 hydrogens. We're adding heat and we form heptane plus 2x. Okay, so you'll see here heptane is 7. We just looked at that. It's 7 carbons. So this would be C7 and something, right? C7. So what's happening is we're actually breaking apart this carbon. Okay, we're breaking apart this carbon. So the specific type of reaction there is also we're doing it with heat. Okay, we're doing it with heat. So it's thermal cracking. Thermal cracking. So cracking is when you split a organic compound into smaller organic compounds. Okay. And it's thermal cracking because of the heat element over there. You don't necessarily have to say thermal. If you just said cracking, you would get that mark, 1 mark. Okay. And they say give the IUPAC name of compound X. Okay, so here this is C13H28, right? And this is heptane. So we know it has 7 carbons, right? So let's actually write out what this heptane is. So I'm going to rewrite our reaction over here, but I'm going to put it in the same form so I can see how many carbons we have. Okay, so heptane is C7H 14 plus 2, 16. Okay, so you remember this is an alkane. So for alkanes, you have the general formula where CnH2n plus 2. That is the general formula for the general form for alkanes. Or you could have drawn heptane. So you would see CC 2, 3, 4. And if you add here, we got 1, 2, 3. Let me do a different color. If we add the hydrogens 3, 5, 7, 9, 11, what are we now? 13, 14, 15, 16. Okay, so that's how we get that 16. Okay, now we have plus 2 times something. So obviously we know this compound is going to be an organic compound, so it's going to be C something. So how many carbons are we left over here? If we do 13 minus 7, we see that we're 6 carbons short, okay? But we have 2 times this. So this has to be a 3, okay? Because we were 6 carbons short, and if we take 2 times 3, we get 6, okay? Now we need to investigate how many hydrogens we're short. So over here, we're short 12 hydrogens. Okay, we're short 12. So this needs to be a 6, because 2 times 6 is 12. Okay, and now we know that this thing is our compound X. This is compound X. So we'll see here that we have 3. So the prefix of 3 is prop. But you'll see that this thing is an alkene. If you draw it, you'll see that it's an alkene. Or you could remember the general formula for an alkene is CnH2n. Okay, but again, if you draw it CCC, and if you have 6 hydrogens, you'll see that actually you're going to have a double bond here. Okay, so like this, because this thing will have 6 hydrogens. If I fill them in over here, you'll see that there's 6 hydrogens. 1, 2, 3, 4, 5, 6. Okay, so it's propene, because it's an alkene, so propene. Okay, good. Next one. So here we're given butane and but1-ene are both colorless gases at room temperature. Each gas is bubbled through a separate solution of red-brown bromine water. Okay, so butane, I don't know why I keep saying butane over here is an alkane. This is an alkane. And this but1-ene is an alkene. It's an alkene. So it says, describe by means of observable changes how one can distinguish between butane and but1-ene. Okay, so what we can call this is, well, this test that we do here is test of saturation. Okay, so if it's saturated, that means that it's alkane, so it's only single bonds. Okay, but if you bubble something that is not saturated, things with double or triple bonds, what happens is through bromine water, the bromine will react with the organic compound, and it will actually be an addition reaction. Okay, so the alkene will no longer be an alkene, it will change into a haloalkene. Okay, not a haloalkene, sorry, a haloalkane. Okay, but this is called a test of saturation. So again, this is a memorization aspect. Okay, so with the butane gas, what's going to happen there in this test tube 1 is it's not really going to react. Okay, so the color will remain. Okay, so for the butane color will remain. Okay, maybe that's not a bad mnemonic over there. So butane, the color remains. Okay, so there'll be no reaction there. Okay, because it's saturated. The color remains for butane. Then for but1-ene, what happens is the color is going to fade. Okay, so the color, but it also disappears very quick. Okay, so the color disappears quickly because there's one S there, disappears. So the color disappears quickly because it is this alkene is reacting with the bromine water and is forming a haloalkane. So we're getting rid of the bromine. We're basically sucking up that bromine, okay, because we have but is what, 4. So essentially we have this thing over here where this is a bromine, sorry, not a bromine, but1-ene. So this is a double bond over here. So we have 2 hydrogens. Okay, this one does not look like that. That one's got 1 hydrogen. This has got 2, that's got 2. Okay, so this is but1-ene that I've just drawn over here. So here's but1-ene. Okay, but what happens when you bubble this through, we're going to have an addition reaction. So this double bond is going to fall away. And what happens is the bromine is going to be added over here. So you see how this bromine water, so while these are the gas molecules, right? But what happens is this bromine in the solution that is making it orange is now going to react with, so let me put Br. So the Br in this solution is going to react with this but1-ene gas, and it's going to then form this compound over here, this haloalkane. So that's why the color disappears quickly. Okay, so yeah, you have to say that the color will remain, and with the but1-ene, the color will disappear quickly. Okay, and the color will disappear quicker for but1-ene. Okay, cool. Now, let's say give the general name for the type of reaction between butane and bromine in the presence of UV light. Okay, so this is again memorization, but now it's the general type butane and bromine in the presence of UV light. Okay, so excuse me, when you have an alkane like butane and it's in the presence of a halogen like bromine, and it's with the condition of when we have the UV light, what happens is converting into a haloalkane. So it's a substitution reaction. You're substituting that H now with a halogen. Okay. So what happens then is the general type of reaction is a substitution. Okay, substitution. Now they ask to write the balanced chemical equation using condensed structural formula for the reaction of but1ene with bromine. Okay, so I would do the structural first, not the condensed. I would do the structural. So if we do but1ene, I've already done it, but I'll do it again first. Okay, we have a double bond here, and so this gets 2 hydrogens, this gets 1 hydrogen, and this gets 2, and this one gets 3. Okay, so what happens here is we've already discussed it's an addition reaction, so this double bond will fall away. And yeah, let me draw it below. So then what happens below is that double bond falls away. So the H's remain, but now you're adding a bromine. H, and like such. Okay, we have added a bromine. Okay, and actually we add 2 bromines. Okay, because obviously this hydrogen over here, well, that hydrogen was there. Okay, so this hydrogen stays up here. Okay, so what I did before is I had an extra hydrogen down here that didn't exist before. But what happens is you add 2 bromines. It's actually what happened. Okay, because these, you'd have to have the same amount of hydrogen. So here at the top we have 8 hydrogens, and here at the bottom we have 2, 3, 4, 5, 6, 7, 8. So the same amount of hydrogens, but what happens is this double bond falls away, you get a bromine there, and then obviously you need a bromine here as well. Okay, so that's what happens. Okay, so this thing is going to be on the reactant side, and then this will be on the product side. So on the reactant side, but remember we're using condensed structural. Okay, let me make sure this is what we have, the but1ene. Okay, in condensed structural. So what we have there is we have this CH2, okay, double bonded with CH, and then we have CH2 and CH3, okay, and that's what we have over there. Okay, and then that reacts to form. So, well, obviously we also need the bromine. Okay, and remember bromine gas is diatomic, so Br2. Okay, then that reacts to form, and over here what we have is CH2, Br, and then we have CH, Br, and then we have CH2 and CH3. Okay, so that is the condensed structural formula. You'll see that the memo is they just put this double bond on the other side. Okay, but you see it will be the same thing, just flipped. Okay, but you get the exact same as condensed structural. It's just flipped, as I said before. Okay, cool. So if you're following along with the memo, don't let that confuse you. All right. Now, for this next question, they say for the reaction question 4943, which is what we've just done here, the activation energy is this amount of kilojoule per mole, and the energy released when the products form is this over here. So the energy out is this amount over here. So you'll see the energy out is greater than the activation energy. Okay, so it's greater. So to find the delta H, right? So what we do is the change in enthalpy. What we do is we say the activation energy minus the energy out. Okay. So that will see, okay, are we releasing energy or taking it in? Okay. So the activation energy was 4795. And the energy out or released was 4889. Okay, And when we subtract those, you'll see we get negative 94 kilojoule per mole. Okay, so the exact same units as we had up here. It's the same units. All right, so you weren't expected to know the units of enthalpy, but obviously if we just subtract those, we get those units, still the same units. Okay, so what this is saying is we have a negative enthalpy. Okay, so we have delta H is less than 0. So when delta H is less than 0, we know we have an exothermic reaction. Okay, so the activation energy, we can think about, say the activation energy was 100. Okay, but what we do is we release 200. So you see how we're taking energy away from ourselves and putting it into the system. So that's why it's exothermic. Okay, we absorbed that 100 and then shot back 200. Okay, in my example. Okay. So what we have to do is we have to complete the energy profile graph for the reaction on the axes provided. Okay. So we know that it's going to have this general form. Okay. We always know it's going to have this general form. Okay. So it's going to have this general form where the energy increases. Okay. But we know that we're releasing energy. Okay. So we started with this energy. We took in the activation energy, but then we released more. So do you see how the energy of the products has to be below the energy of the reactants because it's exothermic? All right, so it will look like this. Okay, more or less. So that is the energy profile graph for the reaction the axes provide. Then they say that we have to label the two energy intervals EA, the activation energy, and delta H on your graph. It is not necessary to show the numerical values. Okay. So activation energy is literally just what we can do is we can draw so that line's a bit higher, but we can just draw a dotted line to the axis over here. Okay. And then the energy we take in to reach the activated complex over here is our activation energy. So that's our activation energy. And then to find the enthalpy, it's just the difference from the reactants to our products over here. So this is essentially the energy we lost. Okay, so this is the delta H. Okay, so it's an exothermic curve. You can memorize this again from your notes. You would see that you'd memorize these from your notes. It doesn't often, I don't think it's very much included in the syllabus of matric. It's mostly done in sort of grade 10 and 11. So yeah, you see it's important that you revise stuff from previous years as well. Okay, and that is the end of the past paper. So I hope it was helpful and I hope you guys enjoyed. And again, sorry if my explanations were a bit all over the place, and I know we did a lot of sidetracks, but if it was helpful, if you guys have any feedback and you felt like you didn't like anything, I'm more than happy for you to give me some constructive criticism. More than happy, I welcome it, and obviously it makes me better, and I would obviously want to make the best videos for you guys. So let me know, and otherwise, all the best, guys.